Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe comes quietly into focus while you rest. Tonight, we're going to float through one of the gentlest, strangest questions in all of cosmology. A question so enormous it reaches beyond stars and galaxies, yet so subtle it hides in the very emptiness between them. What shape is the universe? And more curiously, why does it appear to be flat? It's a strange thought, isn't it? The idea that the whole of existence could have a shape at all. After all, when we look up at the night sky, we don't see an edge or a curve or a boundary. We just see darkness stretching endlessly, a quiet scatter of light resting on a black canvas. But physicists will tell you that space itself, the invisible fabric holding every star and every atom in place, can bend, twist, and stretch. And the way it does, or doesn't, reveals something profound about how everything began, and perhaps how it might all end. Before we drift too far into cosmic geometry, take a breath and settle in. Maybe you're lying in bed, lights dim, the faint hum of the night around you. Maybe you're listening from somewhere far away, on a train, or in the soft half-silence of early morning. Wherever you are, this moment exists inside the same vast universe we're about to explore, and its shape, flat, curved, or infinite, is quietly shaping you too. If you find these kinds of calm cosmic wanderings soothing, I'd be grateful if you tapped that little like button, maybe subscribed, or shared this space with someone else who might need a gentle dive into the deep. It helps this quiet corner of science find other curious night thinkers, people like you, who wonder just before sleep about the things that stretch beyond sight. So now, let's begin, slowly and simply. Imagine for a moment the surface of the Earth. Stand on a wide plain, and it feels flat. You can walk for miles and never sense a curve beneath your feet. But if you could fly high enough, the horizon would start to bend, the world folding softly beneath you into the arc of a sphere. Our universe, in its own way, tempts us with the same illusion. On the scale of galaxies, on the scale of everything we can see, it looks flat, perfectly balanced. But could it be that it only appears flat because we're standing on a cosmic plane so immense that any curve is hidden by its size? Scientists call this flatness, but it's not the kind of flatness you'd find on a table or a map. It's a mathematical kind. It describes the geometry of space itself, the invisible scaffolding on which all matter rests. If the universe were curved positively, like the surface of a sphere, then space would gently bend back on itself. If it were curved negatively, like a saddle, space would curve outward, expanding faster than straight lines can keep up. But flat space is the delicate middle ground. It means that the rules of Euclidean geometry, the kind you learned in school, with triangles adding up to 180 degrees, still hold true, even across cosmic distances. For a long time, scientists didn't know what to expect. In the early days of cosmology, when people first realized the universe was expanding, it seemed just as likely that gravity might someday slow that expansion and pull everything back together. In that case, the universe would be curved inward, like a giant sphere collapsing under its own weight. Or, if there wasn't enough matter, maybe gravity would never win, and the universe would keep expanding forever, curving outward like an open saddle. But as we began to measure, and measure more precisely, the results kept pointing towards something uncanny, a universe that was not curved much at all. Within the limits of our most sensitive instruments, it seemed almost perfectly flat. That word, almost, matters. Because flat doesn't mean perfectly flat, only that it's so close that we can't yet detect a deviation. If there is a bend to the cosmos, it's so gentle that even light, travelling for billions of years, hasn't yet revealed it. And that's both astonishing and deeply puzzling. Because according to our understanding of how the universe began, it shouldn't be this flat. The early universe was chaotic, hot, and dense. Any tiny irregularity should have grown over time, making space visibly curved. Yet here we are, living in a universe balanced to one part in many trillions, so balanced that if the early density had been just a hair different, it either would have collapsed back into itself or expanded too quickly for galaxies to form at all. So how did it find that balance? Did something fine-tune the cosmos? Or is there a natural reason, some grand physical process, that smoothed everything out? These are the questions that have kept cosmologists awake for decades, staring at faint glimmers of ancient light and wondering why the universe seems so delicately poised on the edge between curve and flatness. When we say the universe is flat, what we're really describing is the relationship between space, matter, and energy. Space doesn't exist on its own. It bends and stretches depending on what's in it. This is the essence of Einstein's general relativity. Matter tells space how to curve, and space tells matter how to move. Picture a trampoline with a bowling ball resting in the centre. The fabric dips, and a smaller ball rolling nearby will spiral inward. That's how gravity works. Now, imagine that trampoline stretched to cosmic proportions, filled not with planets and stars, but with clusters of galaxies and vast invisible clouds of dark matter. The question becomes, is that cosmic trampoline flat, or is it curved? And if it's flat, what's keeping it that way? One way to tell is by watching light itself. Light always travels along the straightest possible path through space, but when space is curved, those straight lines aren't what we think they are. If the universe were curved like a sphere, the paths of light would eventually converge, like lines of longitude meeting at the poles. If it were curved like a saddle, those lines would diverge, spreading farther apart. By studying how ancient light from the early universe spreads across the sky, scientists can test which kind of geometry fits best, and again it comes back flat. But before we go there, before we talk about that ancient light and the incredible clues it carries, it's worth pausing on something simpler. The idea of flatness sounds mathematical, even cold, but it's also philosophical. To say the universe is flat is to say it's balanced between extremes. It's neither collapsing nor flying apart too quickly. It's a universe that somehow found the middle path, like a tightrope walker balancing across infinity. That balance, fragile and astonishing, is the reason you and I can exist at all. Because if it were tilted even slightly one way or the other, atoms would never have gathered into stars, stars would never have formed planets, and none of this quiet nighttime reflection would be happening. What makes it more fascinating is that this flatness wasn't always obvious. Early astronomers didn't even know the universe was expanding. They saw galaxies drifting away, yes, but the idea that space itself was stretching was a revelation. It took the work of Einstein, Hubble, and others to realize that the galaxies aren't flying through space like sparks from a firework. They're being carried along as space itself expands. Once you understand that, the question shifts. It's not just about where things are, but how the fabric itself behaves. The geometry of the universe isn't drawn on a background. It is the background. It's the stage and the play, the fabric and the story. And that's what makes the phrase, "the universe is flat," so deceptive in its simplicity. Because it doesn't mean flat like a pancake or a page. It means that the rules of motion and light and distance behave as though the great cosmic fabric has no large-scale bend. Local distortions still exist, of course. Every planet, every star, every galaxy slightly warps the space around it. But if you could zoom out far enough, way beyond clusters of galaxies, beyond the great filaments of cosmic structure, what you'd see is equilibrium. A universe where the average curvature is essentially zero. It's a little like standing on an ocean so vast that its surface appears perfectly smooth. You know there are waves, currents, and depths, but from a great height, it all blends into stillness. That's our cosmic sea, locally uneven, globally calm. Yet this calmness raises questions. If the universe began in a fiery explosion, how did it end up so precisely balanced? The Big Bang should have left behind wrinkles, regions slightly more dense or less dense, where curvature would build up over time, And if it started even slightly curved, that curve should have grown and not disappeared. Flatness, in a sense, is unstable. It's like trying to balance a pencil perfectly on its point. Any small deviation would cause it to tip. So how, against all cosmic odds, did our universe manage to stay upright? That's where the story starts to bend. Figuratively, not geometrically, toward deeper mysteries. Because as we'll soon see, the answer to that question may lie not in the present universe, but in its very first moments, when everything we know was smaller than a grain of sand and expanding faster than light itself. For now, let that image settle. A universe vast and seemingly infinite, yet so delicately balanced that its curvature, if it exists at all, hides beyond the horizon of our vision. Flat not because it's simple, but because it's exquisitely tuned. A cosmos that, by all rights, shouldn't have been so even, yet is. And as you rest here listening, consider this. Somewhere, billions of light years away, another observer might be asking the same question, under a different sky, in a galaxy we'll never see. They too might look out and measure, and find that the universe around them feels flat, endless, balanced. The geometry of everything quietly agreeing across unimaginable distance, that the cosmos has found its equilibrium. Because in that equilibrium lies something deeply peaceful, a sense that even in chaos there is structure, even in expansion there is balance, and even as the night stretches on, the universe itself seems to whisper a calm reminder. The curve of everything is quieter than it seems. When you think about space, you might picture something vast and empty, a black background dotted with points of light, stretching without end in every direction. But the truth is far stranger. Space isn't just the emptiness between things, it's a thing in itself, a flexible fabric that can bend, stretch, and curve, shaping everything that moves through it. It's not something you travel across so much as something you exist within, always changing, always shifting beneath the surface of what seems still. The universe, as we understand it, is made not only of matter and energy, but of geometry. That geometry defines the shape of space, and the shape of space tells matter how to move. When physicists say the universe might be flat or curved or open, they're not describing what it looks like to the eye. They're describing how it behaves, whether two beams of light that start side by side will ever meet, whether parallel lines will stay parallel forever or slowly drift apart, whether triangles drawn across galaxies will add up to the familiar 180 degrees, or just a little more or a little less. It sounds abstract, but it's not. Every part of existence is wrapped in that invisible geometry. The shape of space determines the fate of galaxies, the size of the cosmic horizon, even how long the universe might last. And yet, for something so fundamental, we can't see it directly. We only notice its effects. Light bends, time stretches, and paths curve not because there's a visible surface to space, but because the geometry itself quietly changes beneath everything we see. To understand that, it helps to remember that space and time aren't separate things. Einstein showed that they're woven together into a single entity, space-time. You can't warp space without also warping time. That's why clocks run differently depending on where they are and how they move. Near a massive object like a planet or star, time slows slightly because space is curved there. In empty regions between galaxies, time moves a little faster. To exist in this universe is to live inside a constantly shifting web of space and time, invisible but very real. Now, when cosmologists talk about the shape of the universe, they usually mean the large-scale geometry of space-time, the average curvature of the cosmos as a whole. There are three main possibilities, and each one paints a very different picture of reality. The first is positive curvature, like the surface of a sphere. In that kind of universe, if you travel in a straight line long enough, you eventually come back to where you started. There's no edge, just a continuous surface looping back on itself. Imagine living on Earth. You can walk east forever, but you never fall off. The universe could, in principle, work the same way in 3 dimensions. It could be finite but unbounded, a kind of cosmic globe where straight lines are actually gentle arcs. The second possibility is negative curvature, shaped more like a saddle. In that kind of space, parallel lines diverge. Light rays spread apart faster than they would in flat space. The universe would be open, infinite, expanding forever with no chance of folding back on itself. And finally, there's zero curvature, the flat universe. In this version, geometry behaves just as it does in the space of our everyday experience. Triangles have 180 degrees, parallel lines never meet, and light moves in straight paths unless disturbed by local distortions like stars or galaxies. This doesn't necessarily mean the universe is infinite, though it could be. It just means that, on average, across the largest possible scales, the geometry doesn't bend one way or the other. So how do you measure the shape of something you can't step outside of? How can you tell if space itself is curved when you're living inside it? It's a bit like trying to determine the shape of a room while trapped in total darkness. You can't see the walls or the ceiling, but you can send out sound waves and listen for the echoes. The timing and pitch of those echoes would tell you something about the room's shape and size. In cosmology, the echoes come from light, specifically the oldest light in the universe, the cosmic microwave background. That faint glow, stretched and cooled over billions of years, carries the imprint of the early universe frozen into it. By studying how tiny fluctuations in that light appear across the sky, scientists can infer the geometry of space itself. If the universe were curved positively, those fluctuations would appear slightly larger. If negatively, slightly smaller. And in a flat universe, they appear just the right size. When the first detailed maps of this ancient light were made in the early 2000s, the results were breathtaking. The measurements lined up almost perfectly with a flat model. Within the limits of observation, space looked uncurved, not bent inward, not bowed outward. Flat to an accuracy of better than 1 part in 100. That means if the universe is curved, the radius of that curvature is so vast that even light travelling since the Big Bang hasn't traced enough of it to reveal a difference. That result changed cosmology forever. It told us something profound about the early universe, something that hinted at processes we still don't fully understand. Because a flat universe doesn't happen by accident. It's not the natural outcome of a chaotic explosion. It requires conditions so finely balanced that the density of matter and energy had to be almost exactly equal to a critical value. If it had been even a fraction higher, gravity would have pulled everything back inward long ago. If it had been a fraction lower, the universe would have expanded too fast for stars and galaxies to form. The fact that we exist at all means that balance must have been achieved with extraordinary precision. That balance is expressed in an equation cosmologists call omega, the ratio between the actual density of the universe and the critical density needed for flatness. If omega equals 1, the universe is flat. Greater than 1 means closed and curved inward. Less than 1 means open and curved outward. When scientists calculate omega using all available data, cosmic background radiation, galaxy distribution, gravitational lensing, they find a value astonishingly close to 1. Within tiny margins of error, our universe sits right on that line. But that perfection creates its own mystery. Why should the universe be so close to flat now, nearly 14 billion years after the Big Bang? The slightest deviation early on should have grown over time. It's as though you balanced a pencil on its tip during the first second of creation, and billions of years later it's still standing upright. That's not just unlikely, it's almost impossible without some mechanism keeping it steady. And that, as you'll soon see, is where one of the most remarkable ideas in cosmology enters: inflation, a period in the universe's first instant when space expanded exponentially, stretching any curvature so thin that it became effectively flat. But before we reach that concept, it helps to linger for a while in the idea itself, what it means to live inside a geometry that doesn't curve back on itself, a cosmos where every direction leads outward forever. In a flat universe, there is no center, no top, no bottom. Every point is just as valid as any other. Expansion happens everywhere at once. When astronomers talk about galaxies moving away from us, it's not because we're in a special place. Every observer everywhere would see the same thing, other galaxies receding in all directions. That's one of the most quietly beautiful truths in science. There is no privileged perspective. The cosmos looks the same from any corner, to anyone, anywhere. That uniformity is part of what defines cosmic flatness. It tells us that on the grandest scales matter is evenly spread and space behaves predictably. It's also the reason the universe seems smooth and structured at once. There are clusters and filaments of galaxies, yes, but when you zoom out far enough, all that structure dissolves into evenness. The same density, the same geometry, no matter where you look. This concept can be difficult to visualize because we're used to thinking in 2 dimensions. When we say flat, we picture a surface, a sheet of paper, a calm lake, a table. But cosmic flatness refers to 3-dimensional space, the volume in which everything exists. It doesn't mean the universe is a flat sheet floating in higher dimensional space. It means that the geometry inside our own 3 dimensions follows the same rules as Euclidean space. Lines don't bend because of overall curvature, they only bend locally because of gravity from matter. To picture it, imagine an enormous loaf of bread rising in the oven. The dough is space itself. The raisins inside are galaxies. As the dough expands, the raisins move apart, not because they're travelling through the dough, but because the dough itself is stretching. Now, whether that dough is flat or curved depends on how its overall structure behaves. If it were curved inward or outward, the distances between raisins would expand differently depending on direction or location. But in a flat loaf, every direction behaves the same. That's what our universe seems to be doing, expanding evenly, everywhere, without large-scale curvature. The beauty of this realization is that it unites so many different observations into a single picture. The cosmic microwave background, the large-scale structure of galaxies, and even the faint bending of light from distant clusters all align with the same conclusion. The universe's shape on the largest scales we can measure is flat to an astonishing degree. Yet despite that elegance, something about it feels deeply counterintuitive. If the universe is flat, where does it end? Does it end at all? Can something be both infinite and expanding? These are questions that challenge our intuition because we live in a world of finite experiences. Everything around us has edges, boundaries, limits. But cosmology operates on a different kind of logic. The universe could be both finite and unbounded, like the surface of a sphere, except extended into 3 dimensions. Or it could truly be infinite, continuing forever with no edge to reach, just more of the same fabric stretching outward. The truth is, we don't yet know. The observable universe, the part we can see, is limited by how far light has had time to travel since the Big Bang. Beyond that horizon, space continues, but we can't measure it directly. It might curve, it might repeat, it might be part of something far larger than we can imagine. The flatness we see could be local, just a small patch of a grander structure. Still, within that observable patch, the geometry behaves with remarkable consistency. When we measure distances between galaxies, when we model gravitational waves, when we map the afterglow of the Big Bang, all the evidence points toward a universe balanced at the knife's edge of curvature, neither closed nor open, but precisely, delicately flat. As you imagine that balance, it's worth remembering how strange it is that we can even ask such questions. We're tiny beings on a small planet circling an ordinary star, and yet we can measure the curvature of the entire cosmos. By collecting ancient light, mapping galaxies, and comparing equations, we've learned that the universe doesn't curve back upon itself, at least not within the range of our instruments. That's an astonishing achievement, and a humbling one. Somewhere beyond our reach, perhaps space does bend, looping back in ways we can't yet detect. Or perhaps it really does stretch endlessly, flat forever, like an infinite plane of stars. Either way, the shape of space holds every story ever told, every atom that has ever formed, every life that has ever looked up and wondered what lies beyond, and it continues to expand silently, invisibly, carrying us along on its endless wave. So the next time you look up at the night sky, you might think about what you're really seeing. Not just stars or constellations, but the geometry of the universe itself, the shape you can't quite see, yet one that defines everything. Straight lines, steady light, a cosmic balance so perfect it hides its curvature behind infinity. A universe that, at least for now, appears to be perfectly, mysteriously flat. When we look out into the universe, we're not really looking across space. We're looking back through time. Every star, every galaxy, every faint point of light we see in the night sky isn't showing us how it is now, but how it was when the light left it. Light doesn't travel instantly. It takes time to cross the vast cosmic distances. The light from the moon takes a little over a second to reach us. From the sun, it's about 8 minutes. From the nearest star beyond our solar system, over 4 years. And from the most distant galaxies we've ever seen, billions of years. Each photon that reaches your eye is an ancient messenger, carrying the image of something that might not even exist anymore. That simple fact leads us to one of the most profound concepts in cosmology, the cosmic horizon. It's the ultimate limit of what we can see, a boundary not of matter or structure, but of time itself. Beyond it lies everything we cannot observe, not because it isn't there, but because its light hasn't had enough time to reach us. The universe may be infinite, but our view of it is not. Imagine standing on a quiet shoreline, the night perfectly still. The sea stretches out before you, black and endless, but the mist limits how far you can see. You know the ocean continues, but it fades into invisibility. The cosmic horizon is like that fog. It marks the edge of our observable universe, not an edge of the cosmos itself, but the farthest distance from which light has had time to travel to us since the beginning of everything. Beyond that, the universe continues silently, forever hidden behind the veil of time. This horizon isn't static. It expands as time passes because light from farther and farther regions has more time to reach us. But there's a catch. The universe itself is expanding, and that expansion carries distant galaxies away faster than light can close the gap. So, while the observable universe grows, the parts beyond it recede even faster. There are regions of space whose light will never reach us, no matter how long we wait. They exist forever beyond our horizon, part of a universe we can never see, never touch, never know directly. Right now, the radius of our observable universe is about 46 billion light-years. That number is much larger than the universe's age in years, which is roughly 13.8 billion. The reason for that discrepancy lies in the stretching of space itself. As the universe expanded, the distances between galaxies grew. So, the light that left those galaxies billions of years ago has been travelling through an ever-stretching medium. Even though the light's journey took 13.8 billion years, the space between us and its source has stretched so much that the source is now over 3 times farther away than it was when the light began its journey. That distance, 46 billion light-years in every direction, defines our cosmic horizon. Everything we can observe fits within a sphere centered on us, about 93 billion light-years across. But that sphere is not unique to us. Every observer on every planet in every galaxy has their own cosmic horizon. From their point of view, they too are at the centre of their observable universe. Not because the universe revolves around anyone, but because light radiates outward equally in all directions. Every point in space is its own centre. It's a humbling idea. No matter where you are, you can only see so far, and the rest of the universe stretches endlessly beyond that boundary. The cosmos could be infinite, or it could curve back on itself in ways we can't detect. We can't tell, because the horizon marks the limit of evidence. It's the edge of what we can know empirically, beyond which lies only speculation. The existence of this horizon also means that, in a very real sense, we live inside a cosmic bubble. It's not made of matter, but of information. Inside it are all the events and objects whose light has reached us since the Big Bang. Beyond it are events still waiting in silence, their light forever out of reach. And because space is expanding faster than the speed of a light in those distant regions, that silence will never break. There are galaxies out there that existed, shone brightly, perhaps even formed civilizations, but their light is receding faster than it can ever arrive. They will remain unseen, their stories untold, existing beyond all possible observation. This might sound sad at first, that we're surrounded by unreachable worlds trapped within a finite bubble of light. But it's also quietly comforting. The cosmic horizon defines our portion of the universe. It gives us a sense of scale, a reminder that what we can see is enough to tell the larger story. Within this observable sphere, we can trace the history of everything from the first atoms to the birth of galaxies to the slow drift of cosmic expansion. We may not see it all, but we can see enough to understand. When scientists map the cosmic microwave background, the afterglow of the Big Bang, they're essentially looking as far as light allows. That faint radiation is the oldest light we can ever observe. It was released when the universe was about 380,000 years old, at a time when it first became transparent to radiation. Before that moment, everything was so hot and dense that light couldn't travel freely. The cosmos was filled with an opaque plasma of electrons and protons scattering photons in every direction. When it finally cooled enough for atoms to form, light broke free, and it has been travelling ever since. That ancient light fills all of space, a soft background hum in every direction. The farthest visible wall of our observable universe. Beyond that wall lies a time we can never see directly. The first moments after the Big Bang, when the universe was smaller than a grain of sand and unimaginably hot. Those earliest instants are hidden behind the cosmic horizon, yet we infer their story through the traces they left behind. The density of matter, the smoothness of the background radiation, the large-scale distribution of galaxies. Like archaeologists of light, we reconstruct what we cannot see from the evidence that remains. What's fascinating is how the horizon itself changes depending on what we measure. There's the particle horizon, the distance light has travelled since the beginning of time. There's the event horizon, the boundary beyond which no future light will ever reach us. And there's the Hubble horizon, the limit beyond which galaxies are receding faster than the speed of light due to expansion. These horizons define what's visible, what's causal, and what's permanently out of reach. Even within the observable universe, many galaxies we see today are already beyond our event horizon. Their light is still arriving, but the space between us is stretching faster than the light can bridge. Someday their glow will fade from view, not because the galaxies disappear, but because their light will never again reach us. The universe's expansion will carry them away faster than we can keep up. Over immense timescales, more and more of the cosmos will slip beyond our reach until only the nearest galaxies remain visible. The universe will seem to shrink, not because it's collapsing, but because its distant parts have accelerated beyond sight. This realization connects deeply to the idea of flatness. A flat universe expands in a specific way, one that allows light to travel great distances, but still leaves boundaries we can never cross. The geometry and expansion together define how far we can see, how the horizon moves, and what lies beyond it. In a curved universe, the horizon would behave differently. In a positively curved cosmos, light could potentially loop around, allowing us to see multiple images of the same object from different angles, like reflections in a hall of mirrors. In a negatively curved one, the horizon would stretch farther but distort our view. In our flat universe, the horizon is clean, smooth, even, and consistent across all directions. That uniformity is another sign that space really is flat on the larger scales. Still, the thought of a horizon, a cosmic limit, makes us wonder what lies beyond. Does the universe simply continue in the same way forever? More galaxies, more stars, more dark matter and dark energy? Or does it change, bending into dimensions we can't perceive? The truth may never be known because our instruments, no matter how powerful, are bound by the laws of physics. We can only see as far as light allows, and light, even at its fastest, cannot outrun the expansion of space. It's almost poetic in its restraint. The universe shows us just enough to understand that there is more, but not enough to reveal it. Every telescope, every detector, every survey pushes the horizon back a little farther, but the horizon itself keeps receding. The more we learn, the more we realize how much remains beyond our reach. Yet within this finite bubble, there is richness beyond measure. Hundreds of billions of galaxies, each with hundreds of billions of stars. Countless planets, nebulae, black holes and interstellar clouds. Every bit of that contained within a region whose radius we can name, measure, and study. That's not limitation, that's abundance. And in a quiet way, this boundary, the cosmic horizon, gives meaning to observation itself. Without it, without the finite speed of light, everything would appear at once. There would be no sense of time, no unfolding story. The horizon turns the universe into a narrative, with a beginning, a middle, and a future still unseen. It gives us perspective, literally and philosophically. We live inside a visible history, a window into the past that stretches 13.8 billion years deep. Every photon we detect is a line of that story written across the sky in ancient light. So the next time you look up at the night, remember that you're not just seeing stars. You're seeing the edge of time itself, the limit of what can be known, drawn by the reach of light. Beyond that edge lies silence, not emptiness, but the unknown. The universe continues there, indifferent to our sight, expanding forever into the unseen. And perhaps that's fitting. Because part of what makes the cosmos so endlessly fascinating is not what we can see, but what we can't. Even in that unreachable distance, its geometry still matters. The flatness we measure here must continue there, woven into the unseen fabric beyond our horizon. The laws that shape our visible sky shape the hidden regions too. The balance that keeps our universe flat stretches past every photon we'll ever receive. Beyond our gaze, beyond our instruments, the universe continues its silent, balanced expansion. And that, somehow, is comforting. The thought that, even beyond what we can see, the same calm order persists, the same geometry, the same laws, the same quiet rhythm of expansion. The cosmic horizon isn't a wall, it's a reminder that the unknown is part of the universe too, and that what we can't see still shapes what we can. The oldest light in the universe is still shining. It has been crossing the cosmos for nearly 14 billion years, drifting through expanding space, stretched thinner and fainter with every passing epoch. We call it the cosmic microwave background, or CMB for short. Though the name hardly conveys what it really is. It's the faint afterglow of the Big Bang, the cooled remnant of a once blinding fire that filled the entire universe. And within that faint glow lies a record of everything that happened in the first few 100,000 years after time began. It's not just light, it's history written into the geometry of the sky. When you imagine the Big Bang, it's easy to picture an explosion, a single point bursting outward into empty space. But that image isn't quite right. The universe didn't explode into space. Space itself was expanding. In the beginning, all of space was filled with a hot, dense plasma, a mixture of particles, radiation, and energy so tightly packed that light couldn't travel freely. Photons scattered off electrons constantly, unable to move more than a few millimeters before being absorbed and re-emitted. The whole cosmos was opaque, glowing white-hot like the surface of a star. For nearly 400,000 years, that was the state of everything. A bright, dense fog of matter and light. But as the universe expanded, it cooled. The particles that made up matter began to slow, and eventually the temperature dropped low enough for electrons and protons to combine into neutral atoms. That event, called recombination, changed everything. Once atoms formed, light could finally travel freely without constant scattering. The fog cleared, the universe became transparent, and the first light of the cosmos began its long, unbroken journey. That light hasn't stopped travelling since. As space expanded, the wavelengths of those photons stretched. What began as visible and ultraviolet light has been lengthened over billions of years into microwaves, far beyond what the human eye can see. Today, that ancient glow fills all of space, arriving equally from every direction. It's not bright, only a few thousandths of a watt per square meter, but it's everywhere, bathing the universe in a near-uniform background at a temperature of just 2.7 degrees above absolute zero. For a long time, we didn't even know it existed. In the 1960s, two radio engineers, Arno Penzias and Robert Wilson, were working at a communications facility in New Jersey, fine-tuning a large antenna. They kept encountering a faint, persistent noise in their data, a background hiss that wouldn't go away no matter what they did. They checked the electronics, they cleaned the receiver, they even chased away pigeons that had nested inside the dish, thinking the droppings might be the culprit. But the noise remained. What they were hearing was the faint echo of the Big Bang itself, washing through their equipment from every corner of the sky. That accidental discovery changed cosmology forever. Suddenly, the Big Bang wasn't just a theoretical model. It was something we could measure, something that left a tangible trace still visible today. And that trace contained clues, subtle fluctuations, tiny variations in temperature and intensity, that told the story of the universe's earlier structure. At first glance, the cosmic microwave background looks astonishingly uniform. No matter where you point a sensitive detector, the signal is almost exactly the same. But when scientists began to map it with higher precision, they found faint ripples, variations as small as 1 part in 100,000. Those tiny differences are the seeds from which all cosmic structure grew. Slightly denser regions in the early plasma attracted more matter through gravity, eventually forming stars, galaxies, and clusters. Slightly less dense regions became the cosmic voids between them. In those delicate patterns, a map of light older than any star, lies the blueprint of everything we see today. What makes these ripples even more remarkable is how they reveal the geometry of space itself. The CMB doesn't just show us where the universe was slightly hotter or cooler. It shows how those variations are distributed across the sky, and that distribution depends directly on the shape of space. Here's how it works. The early universe wasn't perfectly smooth. Tiny fluctuations in density created sound waves, literal pressure waves rippling through the hot plasma. These oscillations compressed and rarefied matter and radiation, leaving distinct patterns in temperature when the universe became transparent. Those patterns have characteristic sizes, physical distances imprinted in the fabric of space. When we observe them today, their apparent sizes on the sky depend on how space has expanded and curved since that moment. If the universe were curved positively, like a sphere, light from those regions would converge as it travelled, making the hot and cold spots appear larger on the sky. If the universe were curved negatively like a saddle, the light would diverge, making the spots appear smaller. But in a flat universe, the apparent sizes match the true physical sizes exactly. When scientists measured the CMB's fluctuations using satellites like COBE, WMAP and later Planck, they found that the characteristic angular size of these spots matched perfectly with what a flat universe predicts. That's one of the most powerful pieces of evidence for cosmic flatness we have. The geometry of space is written in the sky, encoded in light that has been travelling since the dawn of time, and what it tells us consistently and precisely is that the universe is flat to within tiny fractions of a percent. It's easy to overlook just how incredible that is. We're talking about light that left when there were no galaxies, no planets, no observers, just a glowing fog. That light has travelled for nearly 14 billion years through an expanding universe, and yet when it arrives, it still carries accurate information about the universe's shape. The photons have been stretched, cooled and diluted, but not destroyed. Each one is a witness to creation, still whispering the same geometry it saw at birth. When we map the CMB across the entire sky, the result is a kind of cosmic fingerprint. It shows a pattern of hot and cold regions that look almost random, but aren't. There's a specific statistical structure to them, peaks and troughs in the power spectrum that reflect how sound waves move through the early plasma. Each of those peaks corresponds to a different scale of oscillation, a different rhythm in the universe's first few 100,000 years. The position of the first peak tells us about the overall curvature. The next few tell us about the density of matter, the abundance of dark energy, and the rate of expansion. Together they form a complete picture, a portrait of the universe as it was when it was still young and newly transparent. Every time a new mission has mapped the CMB, the image has become clearer. The COBE satellite in the early 1990s gave us the first rough outline. The WMAP mission in the 2000s sharpened it dramatically, confirming the universe's flatness with greater precision. And the Planck satellite, launched in 2009, brought the view into breathtaking detail, not just confirming the geometry, but measuring the universe's age, composition and rate of expansion with unprecedented accuracy. And yet, for all its precision, the CMB also reminds us of what we can't see. Beyond that ancient light, there's nothing visible, no older photons, no deeper record. The universe before recombination is hidden from direct observation because the light from that time was trapped. What lies behind the CMB can only be inferred through theory and indirect evidence. Inflation, quantum fluctuations, and the birth of the first particles all belong to that unseen era. The CMB is the curtain between the observable and the unknowable. Even so, the light that does reach us carries immense meaning. Its near uniformity tells us that the early universe was astonishingly smooth, the same temperature everywhere to within tiny variations. That uniformity is puzzling because distant regions of the universe could never have exchanged information or energy fast enough to equalize their temperatures before the light we see was released. It's called the horizon problem, and it's one of the key reasons physicists propose the idea of cosmic inflation, an early burst of exponential expansion that stretched space so rapidly that regions now far apart were once close enough to share the same conditions. That stretching would also flatten the universe, ironing out any initial curvature. So the geometry we see in the CMB isn't just a snapshot, it's a clue, a fingerprint left by a process that smoothed and balanced everything we see today. When we study those faint ripples, we're not just looking at light, we're looking at the memory of the universe's first moment of calm, the echo of its transition from chaos to structure. It's humbling to think that such faint radiation holds so much. Every photon in the microwave background has travelled nearly the entire age of the universe to reach us, dodging galaxies, passing through the thin gas between clusters, bending slightly under gravity's pull, yet still arriving intact enough to tell us about its origin. And every time we measure it, we're effectively taking the universe's temperature, listening to its oldest vibrations, and reading the geometry written into the night. If you were to tune a sensitive radio receiver to just the right frequency, around 160 gigahertz, you'd find that about 1% of the static noise you hear is from the CMB itself. That means that every time you see the grainy snow on an untuned television screen, a tiny fraction of that fuzz is ancient light, the glow of the universe's birth still flickering faintly in your living room. It's one of the few ways we can literally see the past, not metaphorically, but physically. The light falling on your eyes or your instruments is the universe itself as it once was, painted across the sky. That realization connects us in a quiet, unexpected way. Every atom in your body, every star you see, every galaxy in the sky, all trace their origins back to that same radiant fog. The CMB isn't just a scientific curiosity. It's the shared background of existence, the canvas upon which everything else was drawn. And as you imagine that ancient light, still crossing space, still filling every direction, you can almost picture the geometry it reveals. A universe that, despite its expansion and complexity, holds itself in perfect balance, flat, even, vast, and quietly luminous. The light doesn't just illuminate the sky, it defines it, shaping our understanding of space, time, and the very structure of reality. That's the power of ancient light. It doesn't just tell us what happened long ago, it tells us what kind of universe we live in now. A universe so finely tuned that its shape, on the larger scales, remains flat and consistent after nearly 14 billion years of evolution. A universe whose first light still whispers across the night, carrying the story of its own creation. And somewhere in that whisper, in those faint microwaves that still hum through the air, is the geometry of everything, the shape of space itself, woven into the quiet glow that never fades. If you were to draw a triangle on a sheet of paper, you wouldn't think twice about what its angles should add up to. You'd expect 180 degrees. It's one of the first things we learn in geometry. A triangle's internal angles always form that neat, predictable total. But that rule, like many things we take for granted, depends on the space you draw it in. In our everyday world, where surfaces are flat and distances behave sensibly, the rule holds true. Yet the moment you start drawing triangles on something curved, everything changes. On a sphere, for instance, triangles can behave in surprising ways. Imagine standing at the North Pole and walking straight down toward the equator. When you reach it, turn 90 degrees and walk east along the equator for a quarter of the planet's circumference. Then turn another 90 degrees and walk straight back to the pole. You've just made a triangle with 3 right angles, 270 degrees in total. That's impossible on a flat surface, but perfectly normal on a curved one. The extra curvature of the sphere adds to the angles. The same principle works in reverse on a negatively curved surface, like a saddle. There, triangles lose angle. Their total adds up to less than 180 degrees. Geometry changes because the space itself is bending. Lines that would be straight on a flat plane either converge or diverge as they move, depending on the curvature beneath them. This simple observation turns out to be one of the most profound tools in cosmology. The universe is far too vast to measure directly, and we can't step outside of it to see its shape. But we can draw triangles, or more precisely, we can look for them in the sky. By measuring how light moves between distant points, and how the angles between them behave, scientists can test whether the space between those points is flat, curved inward, or curved outward. It might sound abstract, but this method is how we know the large-scale geometry of the universe. The cosmic microwave background, that ancient light from the Big Bang, provides a natural way to draw those cosmic triangles, tiny variations in its temperature-marked points of known physical size, created by sound waves in the early universe. By measuring the angles those patterns make on the sky, astronomers can tell whether the space between them is flat or curved. It's cosmic geometry on the grandest possible scale. Let's step back a bit and think about what that means. The early universe was filled with fluctuations, regions of slightly higher and lower density, where matter and radiation danced in a delicate rhythm. Those fluctuations were tiny, but they set the scale for everything that would follow. The sound waves rippling through that hot plasma had a maximum distance they could travel before the universe cooled and became transparent. That distance, called the sound horizon, acts like a ruler imprinted on the sky. When we look at the cosmic microwave background today, that ruler appears stretched by the expansion of space. But its physical length at the time it formed is well understood. So by measuring how large that scale appears in the sky, how big the ripples seem from our point of view, we can deduce the shape of the space the light has travelled through. Here's the logic. If the universe were positively curved, like the surface of a sphere, the light from those ancient ripples would converge slightly as it travelled, making the hot and cold patches appear larger. If it were negatively curved, the light would diverge, making the patches appear smaller. But if the universe is flat, the apparent size of the patterns matches exactly what we'd expect based on their physical size. When astronomers did these measurements using satellites like WMAP and Planck, they found the angular size of those features to be about 1 degree, the same as the width of your little finger held at arm's length. That exact size matched the prediction for a flat universe almost perfectly. If there is any curvature, it's so small that we can't detect it, even with the best instruments we've ever built. So, in a way, we've drawn triangles across the sky, one side defined by the distance to the CMB, one side by the physical scale of the sound horizon, and one side by the angles we measure here on Earth. The sum of those cosmic angles tells us how space itself behaves. And the result is clear. On the largest scales we can observe the universe is flat. The elegance of this technique is that it doesn't rely on guesswork or philosophy. It's geometry, the same geometry you learned in school applied to the entire cosmos. The rules that define a triangle on a piece of paper also describe the structure of the universe, provided we have the patience to measure carefully enough. And what those measurements show is that we live in a universe balanced to extraordinary precision, where the geometry of space follows Euclid's ancient rules even across billions of light years. That doesn't mean everything is perfectly flat everywhere. Local curvature still exists. Planets, stars, and galaxies all warp the space around them through gravity. Every massive object bends the paths of light passing near it. But on average, when you zoom out to scales of hundreds of millions of light years, those local distortions cancel out. The overall shape of the universe, the fabric that contains everything, remains flat to within tiny margins. This discovery has deep consequences. It tells us that the universe's density, the total amount of matter and energy it contains, must be extremely close to a critical value. That critical density determines whether the universe will curve inward, outward, or remain flat. If the actual density were even slightly higher, the universe would have closed in on itself long ago. If it were slightly lower, it would be open and negatively curved. The fact that it sits almost exactly at that dividing line is one of the great cosmic mysteries. Scientists often refer to this as the flatness problem. Why should the universe's total density be so finely tuned to the critical value? There's no obvious reason it should have started that way. In fact, in the standard Big Bang model without inflation, any small deviation from flatness would have grown exponentially over time. To stay flat today, the early universe must have been tuned to within 1 part in 10 to the power of 60. That's a level of precision so absurdly exact that it demands an explanation. The best explanation we have so far is cosmic inflation, a brief but extraordinary period of exponential expansion that occurred in the first fraction of a second after the Big Bang. Inflation would have stretched out any initial curvature the same way blowing up a balloon flattens its surface at small scales. Whatever shape the universe had before inflation, the rapid expansion smoothed it out so thoroughly that today it appears flat across observable space. But we'll come to that part of the story soon. For now, the important point is that the geometry revealed by those cosmic triangles isn't an accident of observation. It's a property of the universe itself, confirmed in multiple ways. Besides the CMB, astronomers use other cosmic rulers to test the same geometry. Patterns in the distribution of galaxies known as baryon acoustic oscillations, the way light bends as it passes massive clusters, and even the brightness of distant supernovae. All of these independent measurements converge on the same result. The universe is flat, with an uncertainty so small that it's practically negligible. The beauty of these methods is their consistency. Each one measures different things: temperature fluctuations, galaxy clustering, light deflection, yet they all point to the same underlying geometry. That kind of agreement is rare in science and deeply reassuring. It means we're not just seeing coincidences, we're seeing the structure of reality revealing itself through multiple independent clues. When you look at it that way, the cosmos becomes an enormous geometry experiment. Every galaxy, every beam of light, every ancient photon from the Big Bang plays its part. The lines they trace, the angles they form, and the distances between them all encode the curvature of space. We don't need to draw those triangles ourselves. The universe draws them for us patiently across billions of years. If you could stand outside it all and look in, which of course you can't, you might see those cosmic triangles stretching across unimaginable distances, linking regions of space so vast that light takes nearly the entire age of the universe to cross them. Yet the relationships between their sides and angles would still follow the same gentle rule: 180 degrees. The universe behaves, in that sense, as though it's drawn on an infinite, perfectly even plane. It's remarkable to think that this simple property, the sum of angles in a triangle, can reveal something so grand. The same rule that governs a classroom drawing also tells us about the shape of space-time itself. That's the quiet power of geometry. It connects the smallest human intuition to the largest cosmic truths. And yet, even as the evidence mounts for flatness, there's still room for subtlety. The data allow for the possibility of an incredibly slight curvature, too small to measure, but perhaps real nonetheless. Some cosmologists think the universe might be very slightly open, with curvature so gentle that it only becomes noticeable far beyond the observable horizon. Others think it might be exactly flat everywhere, the product of inflation's perfect smoothing. Either way, the difference would be minuscule, far smaller than anything that could affect the way we live, or even the way galaxies form. In practical terms, that means the geometry of the universe behaves as flat for everything we can measure. Gravity still works the same way, light still travels in straight lines across cosmic distances, and the expansion of the universe proceeds according to the rules of flat space-time. When we build our models of cosmology, the equations that describe how galaxies evolve and how the cosmos changes with time, we assume flatness not because it's convenient, but because it's true to the limits of what we can see. Sometimes it helps to think of it like sailing across a vast ocean. The water might follow the curve of the Earth, but from the deck of your ship the horizon looks flat. The scale of the curvature is so immense that it disappears from sight. Our universe is like that, except on an even grander level. The curvature, if it exists, is spread across distances so vast that within our observable region, a sphere nearly 93 billion light-years across, it appears perfectly flat. So, when scientists talk about triangles in the sky, they're not being metaphorical. They're describing the literal geometry that reveals the shape of the cosmos. It's an extraordinary act of measurement, and to look at faint ripples in ancient light, translate them into distances and angles, and from that infer the global structure of reality. It's a reminder of how human curiosity can reach far beyond our tiny planet, out into the silent immensity of space, and still make sense of it with the same simple tools we use to draw shapes on paper. The next time you look up at the stars, you might imagine invisible triangles connecting them, lines of light crossing space, forming angles that quietly add up to a clue about the universe's shape. You won't see them, of course, but they're there, woven into the fabric of the night, the geometry of the cosmos expressed in patterns of light, silent but precise, stretching endlessly through the dark. And those triangles, those simple relationships between light, distance and curvature, tell a quiet truth. The universe, for all its complexity and chaos, follows rules that are elegant, balanced and constant. The same geometry that governs a child's drawing also governs the motion of galaxies. And in that harmony between simplicity and immensity, between lines on a page and the shape of the infinite, lies one of the most beautiful facts we know. The universe, it seems, really is flat. Gravity is a quiet thing. You don't feel it working. Not really. It doesn't announce itself with flashes of light or bursts of sound. It just pulls, steady, constant, invisible. It's the force that keeps your feet on the ground, the moon in its orbit, and the planets circling the sun. It's so ordinary that most of the time we don't think about it at all. Yet it's also the most mysterious of all the fundamental forces. It's the one that defines the shape of space, the rhythm of time, and the destiny of the entire universe. To understand why the universe is flat, or nearly so, you have to understand what gravity really is. Not the simple pull we learned about from Newton, but the deeper truth that Einstein revealed. Because in Einstein's view, gravity isn't a force at all. It's geometry. It's the shape of space-time itself. That idea sounds abstract, but it begins from something simple. Imagine placing a heavy ball on a stretched sheet of fabric. The fabric dips under the ball, creating a curve. If you roll a smaller ball nearby, it spirals inward, not because the larger ball is pulling it, but because the fabric itself is curved. The smaller ball is just following the straightest possible path in a distorted space. That's what Einstein realized, that matter tells space how to curve, and curved space tells matter how to move. It's a subtle, elegant relationship. Everything with mass, from planets to stars to entire galaxies, bends the space around it. Even light, which has no mass, follows those curves, bending its path when it passes near something massive. The sun, for example, deflects the light of distant stars slightly as it passes by, an effect first confirmed in 1919 when astronomers observed starlight bending during a solar eclipse. That observation turned Einstein's theory from a bold idea into a proven description of reality. But gravity doesn't just curve space, it curves time as well. Near a massive object, clocks run slower. The stronger the gravity, the more time stretches. You can measure it directly with precise instruments. Even the difference between the top and bottom of a tall building is enough to detect a tiny change in the flow of time. This stretching of time is part of the same geometry. Space and time aren't separate entities, they're woven together into space-time, a single fabric that responds to mass and energy. Now imagine that idea on a cosmic scale. Every galaxy, every cluster, every wisp of dark matter adds its influence, bending and stretching the cosmic fabric. The result is the large-scale geometry of the universe, a vast interconnected curvature created by everything within it. The question of whether the universe is flat, open or closed is really a question about how all that matter and energy balance against the expansion of space. Here's where the trick comes in. Gravity, on its own, always pulls things together. It slows expansion, draws matter inward, and shapes everything from orbits to black holes. But in the early universe there was a delicate competition taking place, a race between expansion and gravity. On one side, the universe's initial momentum from the Big Bang was pushing everything outward. On the other, gravity was pulling inward, trying to slow that expansion down. The balance between these two determines the overall curvature of space. If gravity was slightly stronger, if the density of matter and energy were even a bit higher, the universe would eventually have stopped expanding and collapsed back on itself in a big crunch. That would be a closed, positively curved universe, like a sphere folding in on itself. If gravity were weaker, if there were less matter to pull against the expansion, space would curve outward, open and negatively curved, expanding forever, faster and faster. But if the two forces balance exactly, expansion and gravity cancel out on cosmic scales. The result is a universe that neither collapses nor curves away. A flat universe. That's the delicate equilibrium our cosmos appears to have found. The density of matter and energy is almost exactly the critical value needed to keep space flat. Within the limits of measurement, the two sides of the cosmic equation, expansion and gravity, are in perfect harmony. That harmony is what Einstein's equations describe. They connect the curvature of space-time directly to the distribution of energy and momentum. Every atom, every photon, every dark particle contributes to that curvature. When you sum it all up, you get the geometry of the universe as a whole. It's a single relationship written into the structure of reality, a relationship between what exists and the space that holds it. But there's something quietly surprising about how gravity behaves in this context. We tend to think of it as a strong, dominant force, but on cosmic scales it's incredibly gentle. Compared to the electromagnetic force, it's weaker by a factor of 10 to the power of 36. You can test that right now. A small magnet can lift a paperclip against the entire gravitational pull of the Earth. That's how feeble gravity really is. And yet, because it only ever attracts and never cancels itself out, it becomes the architect of the cosmos. It shapes everything large enough for its weakness to add up over immense distances. In that sense, gravity is patient rather than powerful. It builds its influence slowly, over time. It doesn't push or pull abruptly. It curves, guiding everything along paths determined by the shape of space. When you look at a planet orbiting a star, you're not seeing a tug-of-war between forces. You're seeing motion along a curved path, an object following the straightest line available in the geometry around it. In Einstein's universe, objects don't need forces to stay in orbit. They just move naturally through curved space-time, following its contours like a marble rolling inside a bowl. This shift in understanding, from force to curvature, changes the way we think about the universe's shape. If the universe is flat, that means all the local curvatures created by matter and energy add up, on average, to zero. There are bumps and dips everywhere, like waves on an ocean, but the average surface remains level. It's not that gravity doesn't curve space. It does, constantly, everywhere. It's just that the overall effect, when viewed on the largest possible scale, cancels out. That balance is astonishingly precise. If the total density of matter and energy were even a trillionth higher or lower in the early universe, the curvature would have evolved differently, and space today would be noticeably curved. But somehow, through processes we're only beginning to understand, gravity and expansion have remained locked in a near-perfect equilibrium. That balance doesn't just define the shape of space, it defines the fate of everything within it. If you imagine the universe as a kind of cosmic seesaw, gravity sits on one side, expansion on the other. For billions of years they've balanced each other almost perfectly. But the seesaw isn't fixed. Dark energy, the mysterious force driving the acceleration of the universe's expansion, is slowly tilting it. Gravity still curves space locally, forming galaxies and stars, but on the larger scales, dark energy pushes everything apart. Yet even that acceleration doesn't seem to disturb the flatness. Somehow, the total energy budget, matter, radiation, dark matter, and dark energy combined, still adds up to the critical value that defines a flat universe. It's tempting to think of this as coincidence, but physics rarely allows such accidents without explanation. The inflationary model, which we'll explore later, offers a possible answer. that the universe's geometry was stretched flat in its earliest moments by an enormous burst of expansion. After that, gravity took over, shaping the local details while preserving the overall flatness. In this view, gravity is not just the sculptor of structure, but also the keeper of balance. To see how gravity's gentle trick works in practice, consider the way galaxies form. In the early universe, matter wasn't evenly distributed. There were tiny fluctuations, slightly denser regions where gravity could take hold. Over time, those regions attracted more matter, growing into clusters, filaments, and superclusters. But while gravity built structure locally, the average density of the universe as a whole stayed remarkably consistent. Expansion spread everything apart, even as gravity pulled it together. The two effects balanced in a dance that continues even now. On the scale of a galaxy, gravity is dominant. It binds stars into spirals and spheres, holds planets in orbit, and keeps black holes at the center of everything. On the scale of the cosmos, though, it becomes almost background, a faint curvature that shapes space but doesn't overwhelm it. It's the whisper behind the vastness, subtle but essential. Even light, the fastest thing in existence, feels gravity's touch. When it passes near a massive object, its path bends slightly, a phenomenon called gravitational lensing. Astronomers use that bending to map the distribution of dark matter in the universe. In a sense, gravity leaves fingerprints everywhere it goes, visible not through its pull, but through the way it shapes light. It turns distant galaxies into arcs and rings, distorts their images, and reveals the invisible scaffolding of the cosmos. That same scaffolding, extended across the universe, contributes to its overall geometry. In this way, gravity connects everything. It links the motion of a falling apple to the orbit of a planet, the spin of a galaxy, and the shape of the universe itself. It's the thread that ties together all scales of reality, from the smallest particle to the largest void. And yet, for all its influence, we still don't fully understand it. We can describe it mathematically, measure its effects with exquisite precision, but we don't know how it fits with the quantum world. The other fundamental forces, electromagnetism, the strong and weak nuclear forces, operate through particles and exchange quanta. Gravity doesn't fit neatly into that picture. It's smooth where the quantum world is discrete, continuous where the other forces come in packets. That tension between smoothness and quantization remains one of the great unsolved puzzles of physics. Still, even without a complete theory, gravity's role in shaping the universe's geometry is clear. It's the quiet regulator that keeps the cosmos balanced. When matter gathers, it curves space. When space expands, gravity resists. The result is not chaos, but equilibrium. The flatness we observe today is, in part, gravity's doing. It's patient, persistent shaping of space-time over billions of years. If you look at the universe this way, flatness isn't just a geometric property. It's the outcome of an ongoing relationship between expansion and attraction, between motion and form. Gravity doesn't demand that the universe be flat, but it maintains the conditions under which flatness can persist. It's the invisible hand that smooths the wrinkles, guiding the fabric of space-time toward balance. So when we talk about the universe being flat, we're really talking about gravity's long, quiet work. The way it bends light and time locally, but allows the grand structure to stay even. The way it turns chaos into order without ever shouting. It's the universe's most patient artist, shaping everything gently, silently, endlessly. And perhaps that's the real beauty of it, that something so subtle, so constant, can define the shape of everything. The same force that holds you to the Earth also sculpts galaxies, bends light, and keeps the universe in balance. The same quiet curve that makes a ball fall to the ground determines the geometry of all existence. It's easy to forget that as we go about our daily lives, surrounded by ordinary gravity. But if you step outside on a clear night, look up, and feel that small pull anchoring you to the planet beneath your feet, remember that you're connected through that same pull to everything else. The stars, the galaxies, the unseen dark matter between them, all woven together by gravity's gentle trick, the invisible curve that makes the universe flat. When scientists speak about the shape of the universe, they almost always come back to one number: the density. It's the quiet fulcrum on which everything turns, the measure that decides whether space bends inward, outward, or not at all. Density may sound like a simple concept, something you could calculate by dividing mass by volume, but in cosmology it becomes a delicate balance that defines the universe's geometry, its history, and its fate. It's not just a number, it's destiny, written in mass and light. To understand that balance, picture the universe as a kind of vast scale, one side weighed down by matter and energy, the other lifted by the expansion of space. If the total amount of matter and energy is too great, gravity wins. The universe curves inward, the expansion slows, and eventually everything might fall back together in a great contraction, the so-called Big Crunch. If the density is too low, expansion wins. Space curves outward, stretching endlessly, galaxies racing apart until even light can no longer bridge the gaps. But if the density is exactly right, not too heavy, not too light, expansion and gravity balance perfectly, and the universe remains flat. That exact balance point is what cosmologists call the critical density. It's the dividing line between geometries, the threshold that separates a closed universe from an open one. In Einstein's equations, it's defined by the rate of expansion, the Hubble constant, and the gravitational constant. In simple terms, it's the amount of mass and energy needed for gravity's inward pull to exactly counterbalance the outward momentum of expansion. The beauty of this idea is its precision. The critical density can be calculated from first principles. At the current expansion rate, it's about 9 times 10 to the minus 27 kilograms per cubic meter, less than a few hydrogen atoms in a room the size of a football field. That's all it takes to define the geometry of everything. Space is so vast and matter so thinly spread that even such tiny numbers determine its fate. When we look out across the universe and measure how much matter and energy there is, we find something astonishing. The total comes very, very close to that critical value. Within the limits of observation, the universe's density is precisely balanced. The sum of all visible matter, dark matter, radiation, and dark energy equals the critical density to within a few percent. That means the universe isn't curved inward or outward. It's flat, balanced at the knife's edge between the two. But this near-perfect equilibrium raises questions. Why should the universe be so finely tuned? There's no reason, in the standard Big Bang model, for the total density to be exactly what it needs to be for flatness. Any small deviation in the early universe, just a fraction more or less matter per cubic meter, would have grown over time, leading to a universe that's obviously curved today. Yet the measurements tell us it's not. The density sits right on the critical line, as though it were designed to be there. This is what cosmologists call the flatness problem, one of the great puzzles in physics. To stay so close to the critical density after billions of years, the early universe must have been unimaginably precise in its initial conditions. Even a difference of 1 part in 10 to the power of 60 at the beginning would have caused it to diverge dramatically by now. That level of precision defies coincidence. Something must have acted to bring the density into balance, a process that smoothed and stretched the universe in its first instant, flattening out any curvature. The leading explanation is cosmic inflation, an era of exponential expansion that occurred a fraction of a second after the Big Bang. But the deeper story of inflation comes later. For now, it's enough to see that balance is both a fact and a mystery. What makes the critical density so fascinating is that it ties geometry and destiny together. If the total density of the universe changes, so does its fate. A dense universe would eventually stop expanding and collapse. A sparse one would expand forever, thinning out until stars burned out and galaxies drifted apart into darkness. But a flat universe, balanced at the critical point, is neither doomed to collapse nor destined for runaway expansion. At least not in the simple models. It's poised between them, expanding forever but slowing asymptotically, like an arrow that never quite stops. For much of the 20th century, cosmologists didn't know which of these fates awaited us. They measured galaxies, counted stars, estimated masses, and found that visible matter made up only a small fraction of what was needed for critical density. That suggested the universe might be open, destined for eternal expansion. But then evidence for dark matter began to appear, invisible mass detected only by its gravitational influence. When galaxies rotate, their outer stars move faster than they should based on visible matter alone. Something unseen must be adding to their mass. That something, whatever it is, makes up about 27% of the universe's total energy content. Even with dark matter included, though, the numbers still fell short of critical density. The universe looked like it might be open and negatively curved, until another discovery changed everything. In the late 1990s, astronomers studying distant supernovae found that the expansion of the universe wasn't slowing down as expected. It was speeding up. Something, a form of energy inherent to space itself, was driving this acceleration. They called it dark energy. Dark energy now accounts for about 70% of the universe's total energy. It acts as a kind of negative pressure, pushing space apart rather than pulling it together. When you add dark energy to the equation, the total density jumps right back up to the critical value. The missing mass wasn't missing after all. It was hidden in the vacuum itself, a property of space that resists compression. That discovery didn't just explain the acceleration, it completed the balance. The combined effects of ordinary matter, dark matter, and dark energy bring the universe's total density to almost exactly 1, the value needed for flatness. It's as though all the pieces of the puzzle fell into place, each component contributing its share to maintain the perfect geometry. This realization reframed the question of destiny. In a flat universe dominated by dark energy, expansion doesn't slow down and stop. It continues forever, accelerating gradually. Galaxies drift farther apart until, over unimaginable spans of time, their light can no longer reach one another. The night sky, once filled with stars, will eventually fade. Future observers, billions of years from now, will look out and see only the faint glow of their own galaxy, surrounded by silence. Yet the universe will remain flat. The geometry doesn't collapse or curl. It stretches endlessly, smooth and calm, even as its contents drift apart. It's a quiet kind of fate, not an explosion, not a collapse, but a slow dimming. The energy that drives expansion will thin the fabric of space but preserve its flatness. The density will stay near critical, even as matter becomes increasingly dilute. In that far future, the balance will persist, not through active tuning, but because dark energy dominates the dynamics. Gravity will no longer be able to gather matter into new stars or galaxies. The universe will grow still, but its shape will remain the same, a flat, infinite calm. When cosmologists talk about this balance, they often express awe at its precision. The numbers align with uncanny accuracy. The measured curvature of space is within 1 part in 1,000 of 0. The total density parameter, usually denoted as pfx, omega, equals 1 to within a fraction of a percent. These aren't random coincidences. They're clues that the laws of physics contain mechanisms we still only partly understand. Mechanisms that allowed such balance to emerge naturally, rather than by chance. But even if we don't yet know why the universe found this balance, we can see what it means. It means that geometry and destiny are two sides of the same coin. The shape of space tells us not only where we are in the cosmic story, but where that story leads. A flat universe expands forever. A curved one closes in on itself. The density and its relationship to gravity and expansion determines which path the cosmos follows. That connection between density and fate gives the universe a kind of narrative symmetry. The same laws that governed its birth will govern its end. The same delicate balance that allowed galaxies to form will also decide how they fade. Every stage of cosmic evolution, from the first light to the last darkness, is written in that equation linking energy, expansion, and curvature. You can think of it this way. If you could somehow pause the expansion of the universe and weigh everything inside it, every particle, every photon, every dark component, the total energy would equal the critical amount needed to make space flat. Nothing more, nothing less. The scales would balance perfectly. That's the essence of the universe we live in. Poised, even, balanced to the edge of infinity. And yet, the balance doesn't feel mechanical or static. It's dynamic, living. It shifts subtly as the proportions of matter, radiation, and dark energy change over time. In the early universe, matter dominated, and gravity's pull was strong enough to slow expansion significantly. As the universe expanded and matter thinned out, dark energy began to dominate, pushing the expansion faster. Through it all, the balance of total density stayed near critical. The universe adjusted itself as if guided by an internal harmony. That harmony doesn't require intention. It's simply the outcome of physics, the natural result of equations that tie geometry to energy. But to our human perspective, it feels like something more profound. We're witnessing a cosmos that, from its earliest moments, has maintained a balance precise enough to allow stars, planets, and life to exist. If the density had been just a little higher, the universe might have collapsed before galaxies could form. If it had been lower, matter might never have gathered at all. Somewhere between those extremes, in the razor-thin range that allows both expansion and structure, we found ourselves. Every breath you take, every ray of sunlight, every glimpse of a distant galaxy happens because the universe's density sits exactly where it does. It's the quiet background condition that makes everything else possible. Without it, there would be no stars to shine, no time to unfold, no space to explore. The balance between gravity and expansion isn't just a mathematical curiosity, it's the reason for our existence. When you look up at the sky and see galaxies scattered across billions of light years, you're seeing the evidence of that perfect balance. Each of those galaxies is both held together and carried apart by forces that have remained in equilibrium for almost 14 billion years. The flatness of space is the silent result of that balance, maintained not by coincidence, but by the gentle interplay of density and expansion woven into the structure of space-time itself. And perhaps that's why the universe feels so calm at its larger scales. Up close, it's full of motion. Stars collapsing, galaxies colliding, black holes spinning, but step back far enough and you see stillness. Not because nothing is happening, but because everything that is happening averages out into perfect balance. The geometry remains level, smooth, infinite. The density and destiny are aligned. The universe, in its vastness, isn't rushing toward chaos or collapse. It's following a path set by the simplest possible condition, just enough energy to be flat, no more, no less. And as it expands, cools and ages, that quiet balance continues. The same gravity that shapes galaxies, the same dark energy that drives expansion, the same critical density that defines the shape of space, all of it locked in an intricate equilibrium that stretches from the first instant of time to the farthest imaginable future. Somewhere, perhaps countless light years away, another observer under another sky might be measuring that same balance, finding the same result, drawing the same quiet conclusion. that the universe is perfectly flat, poised between extremes, and both of you, separated by distance and time, are part of the same geometry, living within the same destiny. A universe held together by a balance so precise it feels almost like grace. There's a moment in the story of the universe that seems to defy everything we know about scale, speed, and possibility. It's the moment just after the beginning, when the universe was so small it could fit in the palm of your hand, and then, almost instantly, expanded to a size far beyond anything we can comprehend. It didn't explode into space. It became space, stretching itself faster than light, smoothing out its wrinkles, flattening its curvature, and setting the stage for everything that would follow. This period is known as cosmic inflation, and though it lasted for only an infinitesimal fraction of a second, a trillionth of a trillionth of a trillionth of a second, it explains some of the deepest mysteries of the cosmos. It tells us why the universe is flat. It tells us why the cosmic microwave background is nearly the same temperature everywhere, and it may even hold the key to why there's something instead of nothing. To grasp what inflation means, you have to first understand what the early universe was like before it happened. Right after the Big Bang, in the first instant of time, the universe was dense, hot, and turbulent. Quantum fields dominated everything. Energy fluctuated wildly, space curved chaotically, and gravity and the other forces of nature had not yet separated into the forms we know today. It was a seething, unstable environment, a sea of raw energy without structure or order. Under those conditions, you might expect the universe to remain chaotic, curved, uneven, full of irregularities. But something remarkable happened instead. A field of energy, now known as the inflaton field, came to dominate the cosmos. This field had a peculiar property. It exerted negative pressure. Instead of pulling things together, it pushed them apart. That negative pressure caused space itself to expand exponentially, doubling in size over and over again in a blink of cosmic time. During inflation, the universe didn't just grow, it stretched. Every tiny patch of space expanded faster than light could travel across it. That sounds like a violation of physics, but it's not. Nothing moved through space faster than light. Rather, the space itself expanded, carrying everything within it outward. The laws of relativity place a speed limit on motion through space, not on the expansion of space itself. In that brief moment, any curvature or irregularity that might have existed before inflation was stretched to near perfect flatness. Imagine inflating a balloon. When it's small, the surface is noticeably curved, but as it grows, the curvature becomes less obvious over any small area. The more you inflate it, the flatter it seems. Inflation did the same thing to the universe, except on an unimaginable scale. If the cosmos had been curved before, inflation made that curvature imperceptible within the observable region. What we now see as a flat universe is the direct result of that expansion. Inflation also explains another puzzle, why the cosmic microwave background has the same temperature everywhere. Before inflation was proposed, this was known as the horizon problem. Distant regions of the universe, separated by billions of light years, have almost identical temperatures, even though they should never have been able to exchange energy or information. There hadn't been enough time since the Big Bang for heat to flow evenly across such distances. Inflation solves that problem elegantly. Before the rapid expansion, the entire observable universe was once a tiny region where temperatures could equalize. Then inflation stretched that region to cosmic size. The uniformity we see today isn't mysterious at all. It's a memory of that early, tiny, well-mixed patch of space, blown up to encompass everything we can observe. But inflation didn't just smooth out the universe, it also planted the seeds of structure, the tiny variations in density that would later grow into galaxies and stars. As the inflaton field decayed and the expansion slowed, Quantum fluctuations within it were stretched across vast distances. Those microscopic fluctuations became the faint ripples we see imprinted in the cosmic microwave background. Over billions of years, gravity amplified them, drawing matter into clusters and filaments. Every galaxy, every star, every planet began as a tiny quantum tremor magnified by inflation. That's the strange duality of inflation. It made the universe smooth overall, but not perfectly smooth. It flattened space while leaving just enough irregularity to give rise to structure. Without those faint differences in density, the universe would have remained a featureless fog. No galaxies, no stars, no life. Inflation made flatness possible, but it also made complexity possible. The physics behind this expansion is still mysterious. We don't yet know exactly what the inflaton field was, or whether it's related to any known particle or force. Some models describe it as a scalar field, a kind of energy that permeates space, similar in some ways to the field responsible for the Higgs boson. Others propose more exotic origins, involving higher dimensions or quantum vacuum states. Whatever its nature, the effect is clear: an enormous release of potential energy, converted into the rapid stretching of space itself. At the end of inflation, that stored energy decayed into matter and radiation, filling the universe with the ingredients for everything that would follow. Physicists call this process reheating, the moment when the cold, empty space left by inflation became hot again, igniting the cosmic fire that we now call the Big Bang. In this sense, the Big Bang wasn't a single explosion, but a transition, a shift from the energy of inflation to the matter-filled universe we inhabit. The evidence for inflation doesn't come from direct observation. It happened too early for light to record it, but from the patterns it left behind. The uniformity of the cosmic microwave background, the flatness of space, and the distribution of galaxies all match what inflation predicts. Even the tiny fluctuations in the CMB's temperature have the exact statistical properties expected from quantum noise stretched by inflation. Every piece of data we've collected points back to that brief extraordinary moment. One of the most striking predictions of inflation is the existence of primordial gravitational waves, ripples in space-time generated by the rapid acceleration of the universe's expansion. These waves would leave a subtle signature in the polarization of the CMB, a faint swirling pattern known as B-modes. Detecting them would provide direct proof of inflation, a glimpse of the universe's earliest vibration. Scientists have searched for these patterns using instruments in Antarctica, Chile, and space. And though they haven't found definitive evidence yet, the quest continues. Each new observation brings us closer to confirming the physics of that first instant. Another implication of inflation is even more mind-bending. Because the process involves quantum fluctuations, it might never have stopped everywhere at once. Some regions of space could continue inflating even now, while others, like ours, have slowed and formed galaxies. This leads to the idea of eternal inflation, a multiverse of universes, each a bubble of space with its own laws of physics, all embedded in an ever-expanding cosmic sea. In that picture, our universe is just one flat bubble among countless others. Whether or not the multiverse exists, inflation gives us a profound sense of continuity. It connects the unimaginably small to the unimaginably large. Quantum fluctuations at subatomic scales became the structure of the cosmos itself. The laws that govern particles inside atoms also shape the geometry of space across billions of light years. The universe's flatness, its balance, its calm, all of it traces back to that fraction of a second when everything expanded faster than thought. To put it in perspective, consider the scale. During inflation, the universe expanded by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. In less than a heartbeat, something smaller than an atom became larger than a galaxy. If you could somehow watch it happen, you wouldn't see an explosion. You'd see space itself stretching, carrying every point away from every other point. No center, No edge, no outward rush, just expansion everywhere, all at once, and the result of that stretching is what we see today, a universe that looks flat, uniform and isotropic on the larger scales. When we measure the curvature of space, we find that it's 0 to within the smallest measurable limits. Inflation predicts exactly that outcome. It didn't erase curvature entirely. It just spread it out so thinly that it's undetectable within our observable region. Beyond what we can see, there might be a larger geometry, slightly curved, perhaps even looping back on itself. But here, where we are, it's flat. The same way a small patch of the Earth's surface feels flat even though the planet is round. Inflation flattened the cosmos in precisely that way, except the radius of curvature is so vast it might as well be infinite. The consequences of inflation reach beyond geometry. It also set the initial conditions for everything that came after. It determined how matter was distributed, how galaxies would form, how the universe would evolve. Without it, the cosmos would look nothing like it does now. It's the quiet prelude that made the symphony possible. Invisible, but essential. Even the accelerated expansion we see today, driven by dark energy, may be a distant echo of inflation. The mechanisms are different, but the effect, space itself expanding at an increasing rate, is eerily similar. Some physicists wonder if dark energy is simply a faint remnant of the same process, a slow continuation of the same stretching that began in that first instant. If that's true, then inflation never truly ended. It only slowed, transforming from a roar to a whisper that still shapes the cosmos. What makes inflation so remarkable is that it takes problems that once seemed insurmountable, the flatness problem, the horizon problem, the origin of structure, and solves them with one elegant idea. It explains why the universe looks the way it does, why it behaves the way it does, and why its geometry is so precisely balanced. It doesn't require fine-tuning. It's the natural outcome of physics operating under extreme conditions. And yet, for all its power, inflation also humbles us. It shows that the universe we see is just a tiny fraction of what exists. The observable cosmos, the bubble we can measure, may be one small patch in an infinite expanse of space. Inflation suggests that beyond our horizon, space continues, smooth and flat, perhaps forever. That means there could be regions of the universe we'll never see, but which obey the same rules, share the same geometry, and expand according to the same laws. If you could step outside the universe, which of course you can't, you wouldn't see an explosion or a sphere expanding into nothing. You'd see an endless, self-similar stretching, space begetting more space, geometry unfolding endlessly. Each patch of space would look flat to any observer within it, no matter where they stood. The flatness we measure here isn't unique to us. It's a universal property of how inflation shapes space-time itself. Even now, billions of years later, we live in the calm aftermath of that great expansion. The galaxies drifting through space, the cosmic background glowing faintly in every direction, the delicate balance between matter and dark energy. All of it is a continuation of the same process that began in that first instant. Inflation wasn't just a moment in time, it was the beginning of geometry, the birth of balance. When you look up at the night sky, what you see is the slow echo of that event. The light from distant galaxies, the evenness of the cosmic background, the flatness of space itself. They're all signs of the same thing, the universe's great stretch. A brief, silent expansion that flattened everything and set the stage for all that would follow. And though it happened long before light existed, long before atoms or stars or life, its effects are still everywhere. Every measurement we make, every observation of cosmic structure, every test of geometry traces back to that moment. The universe's flatness isn't a coincidence. It's the lingering signature of inflation, the memory of a time when space itself expanded faster than light, smoothing out its own curvature, setting the conditions for a calm, balanced cosmos. That's inflation's great stretch. Not a violent explosion, not a beginning from nothing, but a quiet transformation. The universe teaching itself how to be flat, how to be uniform, how to last. And in that briefest instant, it found the balance it still holds today. When you look up at the night sky, you're seeing the present moment. The stars shining now are alive in their current state, their light reaching you after years or centuries of travel. But when we look deeper, far beyond our own galaxy, beyond clusters and filaments of galaxies, we start to see something else. We see the past carved into the light itself. We see ripples frozen in time. These ripples are faint, almost invisible, but they fill the universe. They are the fingerprints of its earlier sound, vibrations left behind in the hot plasma that once filled all of space. Before stars, before atoms, before anything could cool and form, the universe rang with these waves. Pressure and gravity played against each other, creating oscillations that travelled through the dense, glowing fog. The echoes of those oscillations are still with us, imprinted in the light of the cosmic microwave background and in the arrangement of galaxies today. The story begins in the first few 100,000 years after inflation, when the universe was still young, dense and hot. It wasn't empty darkness yet. It was a seething mixture of particles and radiation, a cosmic ocean of plasma where light and matter were locked together. Photons couldn't travel freely because they were constantly bouncing off electrons. Every region of slightly higher density would compress under its own gravity, heating the plasma and increasing pressure. That pressure would push back, expanding the region again. The result was a cosmic pulse, waves of compression and expansion rippling through the early universe like sound waves through air. We call these oscillations acoustic waves, and they filled the universe with an intricate rhythm. Some regions of space were compressed, others rarefied, all oscillating in step with the expanding cosmos. As time passed, these ripples grew larger in wavelength but weaker in strength, gradually freezing in place as the universe cooled. When the first atoms formed and light broke free, the moment of recombination, those waves stopped moving. Their final positions were imprinted into the radiation that flooded out in all directions. That radiation is the cosmic microwave background, and within its faint variations, the pattern of those primordial ripples is still visible. When scientists study the CMB, they don't just see random spots of light and dark, they see a detailed record of those frozen oscillations. The size, spacing, and amplitude of the temperature fluctuations tell us about the sound waves that once travelled through the early plasma. Each peak and trough in that pattern corresponds to a specific mode of oscillation, regions that were at maximum compression or rarefaction when the light escaped. By measuring those patterns precisely, we can read the history of the universe's first vibrations. The physics behind it is beautiful in its simplicity. Gravity tries to pull matter together, radiation pressure pushes it apart. The two effects balance in a dance of oscillation, each tugging against the other. Because the early universe was expanding, these oscillations had only a limited time to play out before the plasma cooled and became transparent. The largest waves completed only a few cycles, while smaller ones oscillated more rapidly. When light finally broke free, each region of the sky froze in the state it happened to be in, some compressed and hot, others expanded and cool. Those frozen ripples became the pattern we now see in the cosmic background. What makes these ripples so important is how precisely they connect theory and observation. When we plot the temperature fluctuations of the CMB on a graph, measuring how much variation occurs at different angular scales, we get a series of peaks and valleys known as the power spectrum. The position of the first peak corresponds to the larger scale of acoustic oscillations, and its location tells us about the curvature of the universe. In a flat universe, the peak appears at a specific angle, about 1 degree on the sky. If the universe were curved, that peak would shift to larger or smaller scales. And when scientists measured it with missions like WMAP and Planck, The peak landed exactly where flat space geometry predicted. The other peaks in the spectrum tell us about the composition of the universe. Their heights and spacing reveal how much ordinary matter, dark matter, and radiation existed at that time. The way those ripples froze in light encodes the entire balance of the early cosmos. From them, we know that ordinary matter, the atoms that make up stars, planets, and people, accounts for only about 5% of the total. The rest is dark matter and dark energy, invisible but real, leaving their signatures in the rhythm of those ancient waves. It's astonishing how much information is contained in such faint variations. The differences in temperature across the CMB are less than 1 part in 100,000. Yet from those tiny ripples we've mapped the universe's composition, its age, its geometry, and even the seeds of its future. The light that fills the sky at microwave frequencies is not just background noise. It's a precise, measurable record of the universe's earliest heartbeat. You can think of those ripples as the cosmic equivalent of fossilized sound waves. They're the last echoes of a time when the universe was dense enough to ring like a bell. The sound itself has long since faded. Space is far too empty now for anything like that to continue. But its imprint remains, frozen in the geometry of light. That's why cosmologists sometimes call the CMB the music of the Big Bang. It's not music in the ordinary sense, of course, but it's a record of vibration, a map of the rhythm that once filled all of existence. And those vibrations didn't vanish when recombination ended. Their influence carried forward into the formation of galaxies. The same acoustic oscillations that left their mark on the CMB also shaped how matter clumped together afterward. Slightly denser regions attracted more matter, forming the scaffolding of cosmic structure. But the pattern of spacing between those regions still bears the signature of those early waves. We can see that pattern today in the large-scale distribution of galaxies, a phenomenon called baryon acoustic oscillations, or BAO. If you measure the average distance between galaxies across vast regions of space, you find a preferred scale, a faint but measurable pattern that matches the size of those primordial ripples. It's as though the universe still remembers its own early vibrations, repeating their spacing in the arrangement of galaxies billions of years later. That's one of the most remarkable things about cosmology, the way the smallest fluctuations in the beginning grow into the largest structures we see today. The galaxies forming along filaments of dark matter, the clusters gathering at their intersections, the great cosmic web stretching across space. All of it began as faint ripples frozen in light. Inflation magnified them. Gravity sculpted them. Time wove them into the structure of everything. Even now, those frozen ripples allow us to test our understanding of the universe's expansion. By comparing the scale of BAO at different distances, scientists can track how fast the universe has stretched over time. It's a cosmic yardstick written into the arrangement of galaxies, one that confirms the same flat geometry revealed by the CMB. The agreement between these two independent observations, one from ancient light, one from modern structure, is one of the strongest pieces of evidence we have that the universe is flat and that inflation's great stretch really happened. But beyond their scientific importance, there's something quietly moving about these ripples. They're a reminder that the universe has always been in motion, even before there were stars or space as we know it. The same oscillations that once vibrated through a dense glowing plasma are the reason we exist. Without them, matter would have spread evenly, and no structure would ever have formed. No galaxies, no Earth, no life. The ripples that froze in light are the blueprint of everything. If you could somehow hear them, if your ears could perceive the pressure waves that filled the early universe, it would have sounded like a deep, steady hum, a single note reverberating through all of space. As the universe expanded, that note would have dropped in pitch, stretching lower and lower until it faded below any possible sound. And yet, in a sense, it still continues. Every photon of the CMB carries part of that vibration, travelling endlessly through the dark, filling the cosmos with a silent harmony, too low for ears but perfect for mathematics. We're surrounded by those frozen ripples all the time. They pass through us constantly, invisible, undetectable without instruments, but always there. The same radiation that once filled the infant universe still fills your room right now, passing through walls, through you, through everything. It's faint but real. A direct connection to the first moments of structure, the first hints of order and chaos. When you consider that, the night sky feels different. It's no longer just a scattering of stars against darkness. It's a tapestry woven from ancient vibrations, the remnants of sound turned to light, still glowing after nearly 14 billion years. Every measurement we take, every map of temperature and structure, every study of curvature traces back to those ripples. They're the bridge between the earliest instant of inflation and the universe we live in now. And what they tell us, again and again, is that the cosmos is flat, not because it had to be, but because inflation made it so, and because those ripples froze in place at just the right moment to preserve that geometry. The light that carries them doesn't just illuminate space, it defines it, recording the distances, the densities, and the delicate balance that keeps everything in equilibrium. If you could look at the sky not as a scattering of stars but as a map of these ripples, you'd see a pattern that stretches everywhere. Faint waves frozen into the structure of space itself. You'd see how every galaxy, every cluster, every void follows their rhythm, and in that rhythm you'd recognize something universal. The calm, repeating pattern of balance that began in the first moments of time and continues still. The universe isn't silent, even now. Its oldest vibration still hums softly, written into the background radiation, encoded in the geometry of the sky. They are the ripples frozen in light, the memory of the universe's first breath, the quiet proof that from its earliest heartbeat, it has always known how to find its balance. When we look at the universe, we see light. Galaxies shine, stars burn, and distant clouds of gas glow softly in the darkness. Everything we can observe directly comes to us through light in one form or another. But as remarkable as it is, the visible universe, the part made of things we can touch, measure, and see, is only a small fraction of what actually exists. The rest, the vast majority, is invisible. And it's this invisible matter and energy that quietly govern the universe's geometry, its motion, and its fate. We call these unseen components dark matter and dark energy, but those names are placeholders more than explanations. Dark doesn't mean shadowy or sinister, it simply means unknown. These are the ingredients we infer from their effects, the way they pull, the way they push, the way they shape the expansion of the cosmos. They're invisible to our eyes and our telescopes, but without them, the universe would look and behave very differently. To see why, we can start with something we do understand: ordinary matter. The atoms that make up you, me, planets, stars, gas and dust. All of it accounts for just under 5% of the total energy content of the universe. Everything we've ever seen, built or measured fits into that tiny slice. The rest, 95%, is dark. The story of how we discovered this imbalance begins with gravity. When astronomers study galaxies, they can measure how far stars orbit their centres. Those motions tell us how much mass the galaxy must contain to keep the stars bound together. But when we add up all the visible matter, the stars, gas and dust, it's never enough. The outer stars move far faster than they should if only visible matter were present. Something unseen must be adding extra gravity, holding those stars in place. The same pattern appears on larger scales. When we look at clusters of galaxies, the galaxies themselves move as if there's far more mass than we can account for in light. Even the hot gas that fills those clusters is held in by more gravity than visible matter can provide. That missing mass, whatever it is, doesn't emit or absorb light, but it bends space and influences motion. That's what we call dark matter, Dark matter doesn't behave like normal atoms. It doesn't collide, absorb, or radiate energy the way ordinary matter does. It interacts primarily through gravity, making it nearly impossible to detect directly. But its fingerprints are everywhere. We see them in the way galaxies rotate, in how clusters hold together, and in how light bends as it passes through massive regions of space, an effect known as gravitational lensing. That bending acts like a cosmic magnifying glass, revealing the hidden structure of dark matter. By mapping those distortions, astronomers can trace the invisible scaffolding that underlies the visible universe. That scaffolding is what allowed galaxies to form in the first place. After inflation, when matter began to cool and gather, dark matter provided the gravitational framework on which ordinary matter could collect. Without it, the small fluctuations in density left by inflation wouldn't have been strong enough to grow into the complex structures we see today. Dark matter made the universe stable enough to form galaxies, yet subtle enough not to collapse everything into one dense mass. It's the quiet architect of the cosmos, invisible but essential. We still don't know what dark matter is made of. Several candidates exist, weakly interacting massive particles, often called WIMPs, axions, sterile neutrinos, or even more exotic possibilities involving extra dimensions. Decades of experiments have searched for signs of these particles in underground detectors, particle colliders, and cosmic rays. So far, none have been confirmed, but the evidence for dark matter's gravitational effects is overwhelming. Even if we don't yet know its nature, we know it's real. It makes up roughly 27% of the universe's total energy budget, more than 5 times the mass of ordinary matter. That alone would be enough to reshape our understanding of the cosmos. But dark matter isn't the only unseen ingredient. There's another component, even stranger, that dominates everything: dark energy. It's not just invisible, it's unlike anything else we've ever encountered. While dark matter pulls, dark energy pushes. It's a form of energy that seems to be inherent to space itself, driving the accelerated expansion of the universe. The discovery of dark energy began with a simple question: how fast is the universe expanding? For most of the 20th century, astronomers assumed that gravity was gradually slowing the expansion. The universe was thought to be decelerating, its initial momentum from the Big Bang slowly reduced by the mutual pull of all its mass. Then, in the late 1990s, 2 independent teams studying distant supernovae, brilliant stellar explosions that can serve as cosmic distance markers, found something completely unexpected. The supernovae were dimmer than predicted, meaning they were farther away than they should have been if the expansion was slowing. The only explanation was that the expansion was speeding up. Something in the fabric of space was acting as a repulsive force, accelerating the separation of galaxies. That something became known as dark energy. It doesn't behave like matter or radiation. It doesn't cluster or dilute in the same way as the universe expands. Instead, it remains constant, or nearly constant, everywhere, at all times. The simplest explanation is that dark energy is a property of space itself, a cosmological constant, as Einstein once proposed and later dismissed. But its true nature remains one of the deepest mysteries in physics. In terms of numbers, dark energy dominates the cosmic inventory. It makes up about 70% of the total energy content of the universe. Dark matter accounts for most of the rest. Ordinary matter, the atoms that make everything we see, is the leftover trace. That distribution shapes not only the universe's structure but its geometry. The balance of these components determines whether space is flat, open, or closed, and when we add them all up, the total comes astonishingly close to the critical density needed for flatness. That's one of the most remarkable coincidences in cosmology, or perhaps not coincidence at all. Inflation flattened the universe in its earliest moments, and dark energy now sustains that flatness as it expands. The two processes, separated by billions of years, act in harmony. Inflation stretched out the initial curvature. Dark energy keeps it from re-emerging. Between them lies the long era of structure formation, when dark matter and ordinary matter shaped galaxies and stars. The result is a cosmos that has remained balanced for nearly 14 billion years. You can think of these three components, ordinary matter, dark matter, and dark energy, as the ingredients of a cosmic recipe. Each plays a distinct role. Ordinary matter provides the building blocks for everything familiar. Dark matter provides the scaffolding that holds those structures together. Dark energy provides the pressure that drives expansion. Change the proportions and the universe would look entirely different. Add more dark matter, and galaxies might form sooner but merge too quickly. Add less, and the universe would be too diffuse for structure to emerge. Change dark energy, and space might either collapse or accelerate so fast that galaxies never form. The balance we observe is just right for complexity to exist. And that balance isn't static. Over time, the relative importance of each ingredient has changed. In the early universe, radiation dominated. Then matter, both ordinary and dark, took over, shaping galaxies and clusters. Now, as space expands, matter becomes more diffuse while dark energy remains constant. Gradually, dark energy becomes dominant, determining the universe's long-term behaviour. In the far future, it will be the only ingredient that matters. Galaxies will drift apart until they can no longer see one another. The night sky will fade and the universe will continue expanding flat and cold. Even though we can't see dark matter or dark energy directly, their influence is everywhere. When we map the cosmic web, we're really mapping the distribution of dark matter, traced by the galaxies that sit within its gravitational wells. When we measure the expansion of space, we're measuring the work of dark energy. Every observation we make, from galaxy rotation to supernova brightness to the cosmic microwave background, points back to these invisible forces. They're the hidden framework of the cosmos, the unseen geometry that shapes all we can see. It's humbling to realize that most of the universe is made of things we don't yet understand. The matter we're familiar with, the stuff that burns, reflects, collides, and shines, is the exception, not the rule. The true nature of reality lies mostly in the unseen, yet we can infer its presence with remarkable precision. We can measure its effects, calculate its density, and trace its influence across billions of light years. We may not know what dark matter or dark energy are, but we know what they do, and that's enough to describe the universe's structure and shape with astonishing accuracy. Sometimes, when you think about that, it's hard not to feel a strange sense of peace. The universe doesn't have to be fully visible to make sense. It doesn't have to reveal every part of itself for us to see its pattern. The invisible and the visible work together seamlessly to create the balance we live within. When you step outside at night and look up, you're seeing only a fraction of what's really there. The stars and galaxies shining back at you are the surface layer of something far deeper, an ocean of invisible structure, held together by dark matter, carried apart by dark energy, perfectly balanced to make the universe flat. The darkness between the stars isn't empty. It's filled with the quiet ingredients that keep everything in place. And perhaps that's the quiet beauty of it all, that the universe's shape, its calmness, its flatness, depends on things we can't see, but can still know. The invisible ingredients define the geometry of existence, not through their brightness, but through their balance. And in that balance, the universe holds its form, expanding smoothly, endlessly, flat and whole. When we say the universe is flat, it's easy to picture something static, calm and unmoving. Flatness suggests stillness, a kind of infinite sheet stretched smooth and silent. But the reality is far more dynamic. The universe is not only flat, it's expanding. Every point in space drifts away from every other, carried outward by the steady stretching of the cosmic fabric. That expansion defines our past, our present, and our future. It gives structure to time itself, and somehow, through all of that motion, the universe manages to remain perfectly flat. It's one of those paradoxes that only seem strange until you understand what expansion really means. When cosmologists talk about the universe expanding, they don't mean that galaxies are flying through space like shrapnel from an explosion. They mean that space itself is stretching, that the distances between stationary points, between galaxies not bound to each other by gravity, are increasing. There is no centre, no edge, and no outside. The expansion happens everywhere, all at once, uniformly. From every galaxy's point of view, all others appear to be moving away. It's difficult to visualize because it's unlike anything in our everyday experience. The closest analogy is the rising of bread dough or the inflation of a balloon. As the dough expands, raisins embedded within it move farther apart, not because they're moving through the dough, but because the dough itself is stretching. Each raisin sees the same thing, all other raisins receding. The universe behaves the same way, only in 3 dimensions and on a scale beyond comprehension. The speed of that expansion depends on distance. The farther away a galaxy is, the faster it appears to move. This relationship, discovered by Edwin Hubble in 1929, became known as Hubble's law. It showed that the universe was not static, as many once believed, but in constant motion. Hubble's measurements of galaxies' redshifts, the stretching of their light toward longer wavelengths, revealed that space itself was expanding. And ever since, astronomers have been refining that measurement, trying to understand not just how fast the universe is expanding, but why and what that means for its shape. The current rate of expansion is described by the Hubble constant, which tells us how many kilometers per second of recession occur for every megaparsec of distance. A megaparsec is about 3.26 million light-years. If the Hubble constant is roughly 70 kilometers per second per megaparsec, then a galaxy 10 megaparsecs away appears to be moving away at 700 kilometers per second, while 100 megaparsecs away appears to recede at 7,000. This relationship holds on large scales, though locally gravity complicates the picture. Galaxies within clusters, bound together by mutual attraction, don't drift apart because the pull of gravity overcomes the expansion of space at those distances. What's remarkable is how the geometry of the universe determines how this expansion behaves. In a flat universe, the expansion follows a specific mathematical pattern governed by the balance between energy density and curvature. If the universe were curved positively, the expansion would eventually slow, stop, and reverse. If negatively, it would accelerate forever without bound. In a perfectly flat universe, expansion continues indefinitely, but the rate changes over time depending on the dominant form of energy. In the early universe, radiation dominated. Photons carried most of the energy, and because radiation dilutes faster than matter as space expands, its influence weakened quickly. Then matter, both ordinary and dark, took over. During that era, gravity slowed the expansion, allowing galaxies and clusters to form. But as the universe continued to stretch, matter spread out and its gravitational influence diminished. Eventually, dark energy, the energy inherent to empty space, began to dominate. Because dark energy doesn't dilute, its effect grows as the universe expands. It's now the main driver of cosmic acceleration. That's why the expansion today is speeding up, even in a flat universe. The geometry doesn't change because of the acceleration. Flatness refers to the spatial curvature of the universe at a given moment, not to whether space is expanding or contracting. You can have a flat universe that's expanding, contracting, or static, depending on the energy content. The key is that its total density remains equal to the critical density. And that's exactly what we observe. It's a delicate balance. The density of matter decreases as the universe grows, because the same amount of matter occupies an ever larger volume. But dark energy stays constant. As space expands, there's more of it, and thus more dark energy overall. The two effects counteract each other in a way that preserves the overall flatness. It's a cosmic equilibrium written into the laws of general relativity, the shape of space adapting naturally to its contents. Even though the universe is expanding faster now than it did billions of years ago, that acceleration doesn't create curvature. The expansion simply scales the distances between points without altering the underlying geometry. Think again of the balloon analogy. You can inflate it quickly or slowly, but the local flatness of a small patch remains the same. The universe's acceleration works the same way. Space stretches faster, but its shape stays balanced. That balance is so precise that, across the observable universe, we can detect no measurable deviation from flatness. Measurements of the cosmic microwave background, baryon acoustic oscillations, and distant supernovae all agree. The total curvature is effectively zero. The universe may be infinite, or it may be finite, but so large that any curvature is imperceptible within our horizon. Either way, it behaves as though it were perfectly flat, and yet, within that flat geometry, everything changes. Galaxies drift apart, clusters thin out. Light from distant objects stretches to longer wavelengths as space expands. What was once visible eventually fades into darkness, carried beyond the cosmic horizon by acceleration. The universe remains flat, but its contents disperse. The stage grows, but the actors move farther apart. It's strange to think that expansion doesn't require anything to push outward. There's no external pressure, no surrounding void for the universe to grow into. Expansion is simply what space does when its energy content demands it. Einstein's equations tie geometry and energy so closely together that the shape of space and its rate of expansion are two sides of the same phenomenon. Change one, and you change the other. That connection means that even though the universe is expanding, it doesn't expand into anything. New space isn't appearing in a pre-existing void. Space itself is the thing that's growing. The distance between any two unbound points increases because the underlying metric that defines distance is changing. That's why there's no edge to the universe, no boundary you could reach by travelling far enough. Wherever you go, expansion looks the same. This idea can feel abstract, but you can trace its effects in everything you see. The redshift of light from distant galaxies, for instance, isn't caused by their motion through space, but by the stretching of space itself. As light travels across the expanding universe, its wavelength lengthens, shifting its colour toward the red end of the spectrum. The farther the light has travelled, the more it's stretched. That's why distant galaxies appear redder and fainter. Their light has been diluted by the growing space it crossed. That redshift carries within it the record of expansion. When we measure it, we're measuring time itself, how much the universe has changed since the light was emitted. Each photon that reaches us has been stretched along with the cosmos, carrying in its length the story of expansion. It's as though space has been recording its own growth in the fabric of light. Even though expansion dominates on the larger scales, local gravity still rules close to home. Within galaxies, within clusters, within the solar system, expansion has no noticeable effect. The gravitational bonds between these systems are strong enough to hold them together. The Milky Way won't drift apart. The Earth won't spiral away from the Sun. Expansion happens between structures, not within them. The distances between galaxies grow, but galaxies themselves remain intact. Over time, though, that distinction will change. As the universe continues to accelerate, regions that are currently connected by gravity will become isolated. The cosmic web will thin. Superclusters will dissolve into lonely islands of galaxies. Eventually, even those galaxies will lose sight of one another as light from beyond their local group redshifts beyond detection. The universe will appear smaller from any given vantage point, though in truth, it will have expanded enormously. The flatness will persist, but the contents will fade. This long-term future, sometimes called the cosmic isolation era, is an inevitable consequence of expansion in a flat, dark energy-dominated universe. It's not catastrophic, it's quiet, a gradual dimming of connection, not a collapse. The geometry remains smooth and balanced, even as the visible structures recede. Space doesn't tear or distort, it just stretches, gently but relentlessly. That's one of the most remarkable features of a flat universe, its resilience. Despite all the motion, all the change, it maintains its equilibrium. Expansion doesn't warp it, acceleration doesn't curve it. The same balance of density and energy that defines flatness continues to hold, even as distances grow unimaginably large. The geometry adjusts perfectly, as though self-correcting, preserving its flatness across eternity. For us existing within that expanding flatness, time feels ordinary. Seconds pass, days unfold, galaxies drift on scales far too vast for us to sense. But if you could somehow see the whole universe at once, you'd witness a slow, elegant transformation. The same geometry stretching, cooling and thinning, but never breaking, never bending. Every part of it still following the same rules, every distant light still bound by the same flatness. It's not a violent process, it's not chaos, it's expansion written into calm, the steady breathing of the cosmos, the same balance that inflation established, that dark energy now sustains, continues quietly, invisibly, moment by moment. And even as the stars fade, even as the distances grow too vast for light to bridge, that balance remains. So when we say the universe is flat and still expanding, we're describing not a contradiction, but a harmony, a geometry that stays smooth while its scale changes forever. The universe doesn't need to bend to grow. It doesn't need to collapse to balance. It simply expands in perfect proportion to its own energy, keeping itself level, endless, and calm. And that, in its quiet way, might be the most elegant thing about it. The universe doesn't fight to stay balanced. It just is. It stretches without strain, moves without motion, expands without edge. A flat universe that's still expanding, infinite, steady, and silent, carrying everything with it through the slow unfolding of time. People often ask what lies at the edge of the universe. It's a natural question. Everything we know seems to have boundaries: the shores of oceans, the outlines of continents, the horizon of the sky. Our minds are used to limits, to edges that separate one thing from another. But the universe, in its quiet, consistent way, doesn't play by those familiar rules. The more you look for an edge, the less you find one. The universe has no boundary you can reach, no wall you could touch, no frontier you could cross to step outside. It doesn't end, it simply continues. That's one of the hardest ideas to accept, because it goes against intuition. When you hear that the universe is expanding, it's easy to imagine it as a kind of bubble growing into empty space, something that has a center and an edge, swelling outward into a larger void. But that image isn't quite right. The universe isn't expanding into anything. Space itself is expanding, and it has no outside. Every point in the universe moves away from every other point, but there is no center where the expansion began, and no edge where it stops. You can imagine it through analogy, though every analogy eventually fails. One of the simplest is the surface of the balloon. If you draw dots on the surface and then inflate it, each dot moves away from the others as the surface stretches. To a two-dimensional creature living on that surface, the universe would appear to be expanding in every direction, even though there's no edge to the surface itself. The surface is finite but unbounded. You could travel around it forever without finding a border. Our universe, as far as we can tell, behaves in a similar way, except it's not the surface of a balloon, but the three-dimensional volume of space that's expanding. If the universe has curvature at all, it's so slight that the radius of that curvature is far beyond the observable horizon. Within the part we can see, space appears flat and unbounded. There's no edge to reach, no boundary where expansion ends, no outside where space gives way to something else. This can feel unsatisfying because we like to imagine the universe as a thing that exists in something, a vast object floating in an even larger void. But in general relativity, space isn't a thing that sits inside another container. It's the geometry of existence itself. There's no background stage on which the universe expands. The expansion is the stage. Space is what distances mean. It's not contained by anything else. Asking what's beyond the universe is like asking what's north of the North Pole. The question sounds reasonable, but it doesn't fit the structure of reality. What's even more fascinating is that a universe can be finite without having an edge. Finite but unbounded, a phrase that sounds contradictory until you understand it. The Earth is like that. Its surface area is finite. You can calculate it, but you can walk forever without falling off. If space itself were curved positively, like the surface of a sphere extended into 3 dimensions, the universe could be finite in volume yet still have no boundary. Travel far enough in one direction, and in theory you could end up where you started, though the distances involved are far beyond any possibility of exploration. In a flat universe, the question becomes even subtler. If space is truly flat and infinite, it has no edge because it goes on without end, infinite in every direction. But if it's only approximately flat, a smooth patch of a much larger curved structure, it might still be finite overall, just vast beyond our comprehension. In either case, there's no wall, no boundary, just continuation. When we look out into space, what we actually see is the past. The light from distant galaxies takes time to reach us, so the farther we look, the further back in time we see. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light years. Beyond that horizon lies more universe, but we can't observe it. It's not an edge, it's a limit of sight. The universe beyond that limit may be much larger, perhaps infinite, but we'll never see it because light from those regions hasn't had time to arrive. That means our observable universe is like a cosmic bubble of visibility, not a bubble of existence. The cosmos continues beyond it, possibly forever. Every observer on every planet in every galaxy has their own bubble centered on themselves. Each sees a different portion of the whole, but the structure remains the same, infinite or unbounded without edges or borders. If you could somehow travel faster than light, which you can't, and move toward the edge of the observable universe, you wouldn't find a wall waiting for you. You'd simply find more galaxies, more space, more time unfolding. And as you moved, your perspective would shift. Your horizon would move with you. You'd always be at the center of your own observable bubble, surrounded by the same vastness. The universe has no preferred center. Every point is equivalent. It's this lack of edges and centers that makes the universe's geometry so beautiful. Flatness doesn't mean flat like a sheet of paper floating in empty air. It means Euclidean. The geometry of straight lines, right angles, and parallel paths that never meet. It means that the sum of angles in a triangle is 180 degrees no matter where you draw it. That geometry extends endlessly, smoothly, without boundary. It's a kind of infinite calm, not a place with borders, but a structure that defines the very meaning of distance and shape. If you stand outside on a clear night, it's hard to imagine this. The sky looks like a dome, the stars like points fixed to its surface. It feels finite, like something you could wrap your hands around. But that's an illusion of perspective, not a boundary of space. The stars aren't painted on the inside of a sphere. They're scattered through 3 dimensions across unimaginable distances. What looks like a dome from Earth is really the edge of your own horizon, the limit of how far you can see, not the limit of existence itself. It's worth remembering that even if the universe had an edge, we might never reach it. The expansion of space means that distant regions are receding from us faster than light. The boundary of what we can observe grows as time passes, But the true extent of the universe may be expanding faster still. There could be vast regions we'll never see, never measure, never know. Not because they don't exist, but because their light will never arrive. And yet, even with that limit, the geometry remains continuous. The same flatness we measure here must extend there. The laws of physics, as far as we can tell, are uniform across the cosmos. The same constants, the same behavior of light and matter, the same relationship between energy and curvature. The universe doesn't change at its invisible edges. It just keeps going, governed by the same quiet order. That uniformity gives the universe its remarkable coherence. It means we can look at one part and understand the rest, at least in principle. It means the equations that describe the geometry of space-time hold everywhere, not just here. When we talk about flatness, we're describing something universal, not a feature of our local region, but a property of space itself wherever space exists. There's a kind of peace in that realization. The absence of an edge doesn't mean emptiness, it means wholeness. It means the universe is complete in itself, requiring nothing beyond it to contain it. It doesn't need an outside or a boundary. Its geometry is self-sufficient. Every point connects smoothly to every other, without discontinuity or break. It also changes how we think about direction. If there's no edge, there's no true up or down, no absolute center to orient ourselves around. The universe doesn't have a privileged point of view. Every observer, wherever they are, sees the same general pattern. Galaxies receding, space stretching, light redshifting. That sameness, that lack of special position, is called the cosmological principle, and it underlies all of modern cosmology. It's the reason we can talk about the universe's shape at all. If space were different in every direction or at every location, there would be no single geometry to describe. The fact that it's uniform allows us to say that it's flat, not here, not there, but everywhere. This absence of edges doesn't just define the universe's structure, it defines how we understand existence. It reminds us that what feels like boundaries are often just limits of perception. The edge of the universe isn't a wall waiting in the distance, it's the edge of time, the horizon of light. Beyond it lies more of the same, continuing without end, governed by the same rules, balanced by the same forces, flat under the same geometry. In a sense, the universe's lack of edges is what allows it to be whole. If there were a boundary, something would have to exist beyond it, a space into which the universe expands, a surface it presses against. But if there's no boundary, if space curves smoothly back on itself or extends infinitely, then the universe is self-contained. It needs nothing outside it to define it. It simply exists, balanced and complete. That's one of the quiet lessons hidden in cosmology. When we imagine the edge of the universe, what we're really touching is the edge of our understanding, the horizon of our sight and imagination. The universe itself keeps going, indifferent to the limits of what we can picture. And in that continuation, there's a kind of serenity. No end, no boundary, just more space, more time, more of the same gentle flatness unfolding forever. If you could travel through that endlessness, you wouldn't feel yourself crossing borders or thresholds. You'd just keep moving, each region of space looking much like the last. Galaxies would thin out with distance, the light would fade with redshift, but the geometry would remain the same. Straight lines would stay straight. Triangles would still add up to 180 degrees. Parallel lines would never meet. The rules would never change. And that might be the most beautiful truth of all, that the universe doesn't need an edge to have structure. Its shape is defined not by where it stops, but by how it continues. Flatness doesn't mean emptiness, it means coherence. It means that the same gentle geometry holds everywhere, from the smallest region we can measure to the farthest we can imagine. So when you think of the universe and wonder what lies at its edge, you can think instead of continuation, of more galaxies, more time, more expansion, all under the same quiet balance. The edge isn't there because the universe never needed one. It's not a boundary that gives space its meaning, but the smooth, endless flatness itself. The cosmos doesn't end. It just keeps unfolding calm and complete into itself. Every time we look into the night sky, we're looking into a mystery. Not just the mystery of distance or time, but of context. The more we learn about the universe, the more a quiet question begins to rise behind all the others. Is this the only one? The laws of physics we see appear universal, the same everywhere we've ever looked. The geometry of space is flat, the constants are steady, the rules consistent. But could that uniformity be a feature of something larger? A single flat patch in a landscape of countless others? That's the idea of the multiverse. It sounds like science fiction, but it emerges naturally from the same physics that explains why the universe is flat. Inflation, the brief, furious expansion that stretched the universe at its beginning, doesn't necessarily stop everywhere at once. The process can continue in some regions, even as it ends in others, creating isolated bubbles of space that expand independently. Each of those bubbles would be its own universe, possibly with its own laws of physics, its own geometry, its own version of reality. Ours might be just one of many, born from the same inflationary sea. To understand how this happens, imagine inflation as a field, a kind of energy spread through space, like a landscape of hills and valleys. During inflation, that field is perched high on a slope, full of potential energy. As it rolls down, that energy converts into expansion, stretching space exponentially. But because of quantum fluctuations, not every region of space makes that transition at the same time. Some patches fall down the slope and stop inflating, creating universes like ours. Others remain on the slope longer, continuing to expand faster than light. In those still inflating regions, new patches can form, each one beginning its own process of expansion. Inflation never truly ends everywhere. It becomes eternal, endlessly generating new universes within itself. In that vast cosmic picture, our observable universe would be a tiny bubble within a much larger multiverse. The light we see, the galaxies we map, the cosmic microwave background we study, all of it would belong to one finite region that stopped inflating long enough for matter, stars, and life to form. Beyond our cosmic horizon, space could continue forever, filled with other bubbles of reality, each one unreachable and invisible to us. It's a staggering idea, but one that flows naturally from the mathematics of inflation. If space can expand exponentially once, there's nothing in the equations to prevent it from continuing indefinitely in other places. The result is a fractal-like cosmos, where universes spawn universes in an endless chain of creation. Each bubble expands on its own, driven by local physics, isolated by the speed of light and the vastness of the inflationary sea between them. In some versions of the theory, those other universes might have the same physical constants as ours, the same speed of light, the same balance of forces, the same flat geometry. In others, they might differ drastically. A slight change in the strength of gravity or electromagnetism could create a universe where stars never form, or where matter never clumps, or where atoms themselves can't exist. In that sense, our universe might be one of the rare few where conditions happen to allow complexity, structure, and life. That's one way physicists interpret the fine-tuning of our universe, the uncanny precision of its balance between density, expansion, and flatness. It's not that the universe was designed that way, but that only universes with that balance can produce observers capable of asking the question. This perspective is called the anthropic principle, and it's not about ego or importance, it's about probability. If countless universes exist, each with different properties, then naturally we find ourselves in one that allows us to exist. A flat universe with stable matter, moderate expansion, and long-lived stars isn't special in design, it's simply one of the few that can sustain observers. In that light, our flatness isn't just a geometric feature, it's a requirement for existence. But not all physicists are comfortable with this reasoning. The multiverse, after all, is almost impossible to test directly. The regions beyond our cosmic horizon are forever out of reach. Light from other universes, if they exist, could never reach us. That leaves us with indirect evidence, the kind of evidence that must be inferred, not observed. Some researchers look for subtle imprints in the cosmic microwave background that might suggest collisions between our bubble universe and others in the distant past. Others study the statistics of inflation, searching for patterns that could indicate eternal processes. So far, the evidence is inconclusive. The multiverse remains a compelling possibility, but not a confirmed reality. Even so, the idea carries a strange and quiet power. It reframes what we mean by everything. For most of human history, the universe meant the totality of all that exists. Now, it might just mean our particular region of a larger whole. Our universe could be local, one domain within an infinite set. The word universe, which once implied completeness, might instead describe only a single chapter in an endless story. And in that story, the geometry of our own universe becomes an illusion of scale. We call it flat because, from our limited perspective, it behaves as such. But what if that flatness is only a small piece of a much larger curvature? Like an ant walking on a vast balloon, we can't perceive the overall shape from where we stand. Inflation might have stretched our patch so thoroughly that it appears flat within our horizon, but on larger scales, far beyond what we can see, the geometry could bend subtly, connecting to other universes through dimensions we can't access. That idea touches on another possibility, that the multiverse isn't just a collection of separate universes floating in isolation, but a deeper structure in which all of them are connected through higher dimensions. Some theories in physics, especially those involving string theory and M theory, suggest that our universe could be a three-dimensional brain, embedded in a higher dimensional space. Other brains could exist alongside ours, each representing a different universe with its own laws. Occasionally they might even interact, colliding or influencing one another in ways that could leave traces in the cosmic background. If this sounds abstract, it's because our language and senses evolved for a very different scale of experience. We're built to understand horizons we can reach, mountains we can climb, seas we can cross. The cosmos operates on scales so vast that even metaphors break under the weight. Yet the mathematics that describes these ideas is consistent, precise, and elegant. The same equations that describe the flatness of our universe also allow for the possibility of countless others. Whether or not those other universes exist, thinking about them changes the way we see our own. It reminds us how much of our understanding is shaped by perspective. To us, the universe feels infinite and complete, but that completeness might be an illusion, a product of our cosmic isolation. We can only see as far as light has travelled since the Big Bang, and within that limit, everything looks uniform, balanced, and flat. Beyond it, the story might be very different, and even if the multiverse remains forever unobservable, it serves a purpose. It forces us to ask what reality means when the boundaries of space and time become uncertain. It reminds us that our universe's flatness, its calm, its balance, may be just one example of many possible configurations. The laws of physics might not be unique, they might be regional. Our constants might be local settings in a cosmic landscape of endless variation. But in the end, whether the multiverse is real or not, its greatest lesson is one of humility. The universe we can see is already immense beyond comprehension, yet it might not be the whole of existence. Our entire observable cosmos could be one tiny patch in a greater expanse, a single flat surface in an infinite mosaic of worlds. That perspective doesn't diminish us, it simply widens the frame, showing that our calm, balanced universe is part of something even larger, perhaps endless in its creativity. And what's remarkable is that even in that vast possible expanse, the same principles hold. The same connection between energy and geometry, the same interplay of expansion and gravity, the same quiet balance that produces flatness. The universe we know is a small piece of a pattern that might repeat endlessly, different forms, different rules, but always governed by the same fundamental relationship between matter, space, and time. When you think about it, the illusion isn't that we live in a flat universe. The illusion is that we think of it as singular. We imagine it as the one and only canvas of reality, when it might be one of many, each shaped by its own balance. The true picture could be far grander, a sea of universes, each expanding, each flat within itself, each frozen in its own moment of balance. We may never prove it. We may never see beyond our horizon. But even that limitation carries beauty. The idea that reality might be infinitely layered, that existence continues beyond what we can measure, gives meaning to curiosity itself. We look, we measure, we wonder, not because we expect to reach an edge, but because every question we ask brings us closer to understanding our own small, flat patch of infinity. And perhaps that's all we need. To know that within the quiet flatness of our own universe lies the same symmetry, the same balance that might echo across countless others. The multiverse, real or imagined, reminds us that the universe we inhabit is both everything and part of something greater, an illusion of completeness that is, in its own way, perfectly true. When we talk about the universe being flat, it can sound like something distant and impersonal, a piece of abstract geometry written into the sky, far removed from anything that touches our daily lives. It seems like the kind of thing that belongs to equations, not to experience. But if you follow that flatness far enough, if you trace what it allows and what it prevents, you start to see that it isn't distant at all. The flatness of the universe is the quiet condition that makes everything else possible. From the existence of galaxies to the air you breathe, to the fact that time itself flows the way it does. If the universe were curved even slightly differently, the entire story of existence would have unfolded another way. Too much positive curvature, and gravity would have overpowered expansion. The universe would have collapsed back into itself long before stars could form. Too much negative curvature, and matter would have spread out too quickly for structure to ever appear. In either case, there would be no galaxies, no planets, no observers to notice anything at all. The fact that space is flat isn't just a detail of cosmic geometry. It's the quiet precondition for everything that happens within it. That balance, the one that holds between expansion and gravity, between density and energy, isn't something we feel directly. We don't sense the curvature of space around us. We live inside it, carried along with it every moment. But everything we see, every law that holds, every process that unfolds, happens because the universe exists in that narrow window of flatness. Stars can burn steadily because the universe is neither collapsing nor stretching so violently that matter can't settle. Atoms can form because space expanded just fast enough to cool, but not so fast that particles couldn't meet. Even the rhythm of time, the steady rate at which cause leads to effect, depends on the same balance that defines flat geometry. It's easy to forget that because the universe's balance feels so stable. We live within its calm as though it were inevitable, but it's not. It's the result of a precise relationship between the total energy content of the cosmos and the rate of its expansion. When those two quantities match exactly, space remains flat. That match has held for nearly 14 billion years. It held through the formation of stars, the gathering of galaxies, the birth of planets, and the emergence of life. It continues to hold now, as the universe accelerates under the influence of dark energy. The balance never slips. You could think of it as a kind of cosmic symmetry, not the symmetry of shape, but of behavior. Flatness allows the laws of physics to work the same way everywhere. Light travels in straight lines, Parallel beams never converge or diverge. The rules that govern atoms are the same in every galaxy, every corner of space. That consistency is why we can understand the universe at all. If space were significantly curved, the laws of physics might vary with location, and the cosmos would be unpredictable, fragmented. But flatness ensures universality. It makes science possible, and that universality isn't just a convenience, it's the structure that lets complexity emerge. Because the universe's geometry is smooth and balanced, small fluctuations can grow without being overwhelmed. Gravity can pull matter together into galaxies without the whole universe collapsing. Energy can spread evenly enough for life to find niches of stability. The calmness we observe on large scales, the even distribution of galaxies, the uniformity of the cosmic background, is what allows chaos and variation to exist on smaller scales. The smoothness creates the conditions for detail. Even the way we measure time owes something to flatness. In a strongly curved universe, clocks would behave differently depending on where they are. Time would flow unevenly, stretched or compressed by the global geometry of space. But in a flat universe, time remains consistent across vast distances. The second that ticks on Earth is the same second that ticks in another galaxy, once you account for local gravitational differences. That uniformity is why we can synchronize cosmic history, why we can talk about events billions of light years apart as part of a single timeline. Flatness also determines how we see. The light that reaches your eyes from distant galaxies travels along geodesics, the straightest possible paths through space-time. In a curved universe, those paths would bend globally, distorting what we see. But in a flat one, light travels predictably. When we map the cosmos, we're not looking through a warped lens, we're seeing the geometry of reality itself. The straightness of space is the reason we can trust what we observe, the reason telescopes can map the sky as though it were a coherent whole. And when you think about it that way, the meaning of flatness starts to feel more personal. It's not just the universe's shape, it's its temperament. A curved universe would be unstable, either collapsing or thinning into emptiness. A flat one endures. It expands steadily, holding structure, maintaining balance. It's the difference between chaos and continuity, between a cosmos that flickers out and one that has time to evolve. Life needs time. It needs stability. It needs a universe that doesn't rush or collapse too quickly. The formation of heavy elements in stars, the slow gathering of planets, the emergence of chemistry and biology, all of these require billions of years of quiet cosmic conditions. Flatness gives that time. It keeps the universe neither too fast nor too brief. It allows evolution, growth, and reflection to occur. In that sense, our very ability to ask about the universe's shape is a product of the shape itself. There's another layer to this, one that's less physical and more reflective. The idea of a flat universe challenges the human habit of thinking in terms of edges, hierarchies, and centers. It reminds us that there is no privileged point of view, no top or bottom, no cosmic center from which everything radiates. Every location, every observer, sees the same general pattern. Galaxies receding in all directions, light stretching with expansion. That symmetry isn't just mathematical, it's philosophical. It means we are not at the center of everything, but we are also not excluded from it. We're part of the same flat expanse, subject to the same rules, connected by the same geometry. There's something profoundly grounding about that. To know that the same laws that govern distant galaxies also govern you. The same constants, the same forces, the same balance. The calmness of space is mirrored in the consistency of everything that happens within it. Flatness isn't a distant abstraction. It's the geometry of connection, the background harmony that allows the universe to make sense. In practical terms, flatness gives us predictability. It allows cosmologists to model the future with confidence. We can calculate how the universe will expand, how galaxies will drift, how light will stretch. The equations work because space behaves uniformly. The future of the universe, its infinite expansion, its cooling, its quiet persistence, follows directly from its flat geometry. That predictability is what allows us to speak of cosmic destiny not as speculation but as science. But there's also an emotional weight to it. Knowing that the universe is flat means knowing that it will expand forever, that there's no cyclical return, no cosmic heartbeat that brings everything back together. It means that time moves in one direction, forward, outward, away. The same geometry that gave us stability also ensures impermanence. The stars that exist now will fade. The galaxies we see will drift beyond view. The night sky will eventually grow dark. The universe's balance allows for both creation and dissolution. That realization doesn't have to feel bleak. There's a quiet grace in it. The idea that we live in a cosmos that has achieved a perfect, lasting balance, one that allows everything to happen exactly as it does. Flatness doesn't mean lifelessness. It means constancy. It means that, within this calm geometry, moments can unfold, stars can burn, planets can turn, lives can be lived. It means there's room for everything that exists, from the smallest particle to the vastest galaxy, to coexist within a stable, infinite frame. It also means that the universe is democratic in a way, the same everywhere, indifferent to location. There's no special place where things work differently. The laws of physics don't privilege any point. You could stand in any galaxy in any direction and measure the same curvature, the same flatness, the same expansion. That universality is the cosmic equivalent of equality. Everything shares the same rules, the same background, the same space, and in that sameness there's a strange comfort. It tells us that no matter where we are, we're part of the same whole. The geometry that shapes galaxies also shapes us. The balance that keeps the universe flat also governs the atoms in your body. The same equations that describe the motion of light across billions of light years also describe the space around you as you breathe. The connection isn't poetic, it's literal. You are part of the same space-time that holds galaxies together and carries light across the void. In that sense, what flatness means for us isn't abstract at all. It's existence itself. It's the reason we can live in a universe that lasts long enough to make meaning, to think, to wonder. It's the reason we can look up and know that the laws of physics don't change halfway across the sky. It's the quiet foundation beneath every experience, every discovery, every question. The geometry of reality isn't curved or chaotic. It's calm and level, and that calmness is the condition for everything we know. There's another way to see it too, not as a set of equations, but as a relationship between chaos and order. The universe began in turbulence, a dense storm of particles and energy. Over time it smoothed itself, expanding into balance. That smoothing gave rise to flatness, and from that balance structure emerged again. Stars, galaxies, life. Flatness doesn't erase chaos. It allows it to exist in a controlled way. It gives the universe the stability to host imperfection. Without it, there could be no story, no evolution, no change. So what flatness means for us is continuity. It means the universe is not fragile. It means that the same quiet balance that governed its birth still governs it now. It means that when you look up at the stars, you're looking at light that has travelled across a geometry so perfectly balanced that it's preserved its path for billions of years. The photons from distant galaxies arrive exactly as expected, following lines that never waver, because space has remained level all that time. That's the quiet miracle of a flat universe. Not just that it exists, but that it endures. It's not a shape frozen in time, it's a state maintained through motion, through expansion, through change. It's dynamic balance, not stillness. The universe is constantly stretching, yet always staying even, constantly aging, yet always obeying the same rules. And somehow, Within that endless balance, there's us, conscious beings who can notice it. We live on a small planet orbiting an ordinary star, in one galaxy among trillions, and yet we can measure the curvature of space to astonishing precision. We can know through light and mathematics that the universe is flat, that it will expand forever, that the same geometry stretches from here to the edge of what's visible. That awareness itself is part of the balance, a fragment of the cosmos becoming aware of its own calmness. Maybe that's what flatness means for us most deeply. It means we belong here, not as accidents, but as expressions of the same symmetry that governs everything. The universe's evenness is reflected in our own ability to perceive order. Its stability is the background that allows consciousness to arise. We are not separate from its geometry. We are made of it. The same space-time that defines flatness defines the space inside and around us. So when you think about what flatness means, you can think of it not as a distant property of the cosmos, but as a quiet truth about existence itself. It means the universe has achieved balance, a balance so precise that it allows everything, including you, to be. It means we live in a cosmos that expands gently enough to give us time to think, to ask questions, to feel awe. It means that the calmness of space isn't out there somewhere. It's here, all around you, woven into the fabric of reality itself. The night sky is never truly silent, though it feels that way when you step outside and look up. The stars hang there, steady and remote, their light crossing millions of years to reach you. The air is still, the ground feels solid, and yet the reality behind that stillness is motion beyond imagining. Galaxies drift apart, space stretches, light redshifts and thins, and the universe continues its quiet expansion through time. But within all that motion, there is a kind of deep calm. The stillness between stars, the silence of balance that the universe has carried since its beginning. When you stand beneath the night sky, you're seeing the afterglow of the universe's great unfolding. The stars you see are the products of that flatness, of that calm geometry that allowed structure to emerge and endure. Each one burns in delicate equilibrium, its gravity pressing inward, its radiation pushing outward, perfectly matched. They are microcosms of the same balance that holds the cosmos itself. The stillness you feel between them is not the absence of activity, but the result of equilibrium on the largest possible scale. If you could somehow watch the universe from outside time, you'd see it like a living map of calm motion, the same geometry unfolding smoothly, each part obeying the same rules, no edges, no breaks. The galaxies would drift like quiet lanterns on a vast sea, never colliding on the grandest scales, only moving apart in steady expansion. The same balance that defines flatness would stretch across everything, connecting the smallest moment of your breath to the structure of the sky itself. That's the thing about the stillness between stars. It's not empty. It's full of space. Space that expands, carries light, bends around mass, and holds the quiet story of the universe's history. Every photon that passes through that stillness is shaped by it. Every bit of matter drifts within it. The emptiness between stars is what gives meaning to everything else. Without it, there would be no distances, no light, no place for galaxies to move, no room for time to unfold. The stillness is not a void. It's the fabric of reality, calm but alive. The stars themselves are fleeting compared to that calm. Each one burns for millions or billions of years, but the universe is far older and will last far longer still. In the distant future, even the brightest stars will fade, their fuel exhausted. The night sky will grow dimmer. Galaxies will drift apart until their light can no longer reach one another. Yet the stillness between them will remain, stretching quietly as space continues to expand. That stillness will outlast everything that shines. When the last stars fade, when matter itself begins to cool toward uniformity, what will remain is the geometry, the flatness, the balance, the structure of space that defines the universe. Even without light, that geometry will endure. The universe will keep expanding, the distances growing, the fabric thinning, but the same calm rules will hold. Straight lines will remain straight, angles will still sum to 180 degrees. The stillness between stars will continue, unchanged, infinite. It's strange to think that emptiness can have structure, but that's what flatness tells us. The vacuum of space isn't truly empty. It has properties, energy, tension, and form. It's the quiet foundation upon which everything else exists. Even as stars die and galaxies vanish beyond one another's horizons, that foundation doesn't disappear. It simply expands, smooth and silent, maintaining its balance. The universe's flatness ensures that this stillness is eternal. That's not a tragic thing, it's peaceful. The end of stars isn't the end of the universe's story, it's part of its rhythm. Creation, transformation, and return to calm. Every particle that burned in a star, every atom that made up a planet, every photon that illuminated space will eventually fade into the same even background. The universe will grow dark, but it will not fall apart. Its geometry will remain perfect, even when there is nothing left to trace it. In that far quiet future, time will still move forward. Space will still stretch. The stillness will deepen but never break. There will be no collapse, no final moment of chaos. The universe's destiny is not destruction, but persistence, an eternal continuation of balance. It will remain flat forever, its expansion endless, its structure unchanging in form. That is the stillness between stars, a universe that keeps existing, calm and complete, long after its contents have gone silent. Even now that stillness is here, though we live in one of the few eras when the cosmos is still bright. We exist in a brief moment when stars fill the night, when galaxies are visible, when light still connects one part of the universe to another. It's easy to take that for granted, to think of the sky as something permanent, but we are living in a window, a fleeting age of light before the long quiet to come. To look up at the stars is to look into that balance while it still glows. And yet, the calm we feel when we look up isn't just an illusion of brightness, it's a reflection of the underlying geometry. The peace of the night sky comes from the same laws that shape the universe itself. The same balance that keeps space flat also keeps the stars stable, the planets in motion, and time flowing steadily. The stillness between stars is, in a way, the stillness within which we live, the condition that allows everything else to happen. You can sense it even here, beneath the atmosphere, standing on solid ground. The pull of gravity under your feet, the hum of distant light in the background, the way space stretches silently all around you. You're part of that stillness, part of the same equilibrium that defines the cosmos. You don't have to go to the edge of the universe to find it. It's here already, in every breath, in every quiet moment, in every particle that moves through space. Because the truth is, there's no separation between the stillness out there and the stillness here. The space between stars extends through everything, through air, through atoms, through you. It's not an emptiness that begins where matter ends. It's continuous. The same fabric that holds galaxies apart also holds the space within you together. The stillness between stars is the stillness that fills all things, and if you think about it, that makes us participants in the same cosmic balance. We're not outside observers looking into a flat universe. We're part of it, moving with it, expanding within it. The same geometry that keeps galaxies drifting apart also allows you to exist in one small corner of it, stable enough to think, to breathe, to look up. The universe's flatness, its stillness, its balance, all of that includes you. Maybe that's why the night sky feels so peaceful. When you look at it, you're seeing the evidence of equilibrium on a scale so vast it's impossible to imagine. The light from distant stars stretched across billions of years arrives exactly where it should because space has behaved perfectly. The universe has held its balance for all that time, never collapsing, never breaking. Every photon that reaches your eyes carries proof of that consistency. The stillness between stars is the stillness of order, of reliability, of a universe that remains true to itself. That calm isn't just out there, in the silence of interstellar space. It's also in the steady laws that let planets orbit, atoms form, and life persist. It's in the geometry that underlies everything, from the vastness of galaxies to the smallest quantum vibration. The universe's stillness is the foundation beneath all motion. It's what allows movement to make sense. Without it, there would be no direction, no continuity, no stability to hold the story of existence together. So when you think of the universe, of its flatness, its expansion, its endlessness, you can think of it as a kind of still ocean. The galaxies are waves upon its surface, temporary and bright, but the ocean itself remains level and endless. The waves come and go, but the calm beneath them endures. That calm is the flat geometry of space, the steady balance of energy, the quiet rhythm of time that continues no matter what rises or fades. It's easy to see the universe as something cold or indifferent, but there's a quiet gentleness in that endurance. The stillness between stars isn't emptiness, it's patience. It's the universe allowing itself to last, giving everything within it the time to exist. The same stillness that will outlast the stars is what made them possible in the first place. It's what makes life possible now. When you stand under the night sky, you're standing inside that stillness. Every breath you take is part of its expansion. Every moment that passes is a continuation of the same calm geometry that began at the dawn of time. The stars shine, but the space between them is what allows them to shine. The stillness is what holds it all together. And maybe that's the quiet truth that lies beneath all of it. That the universe doesn't need to end or begin again, or be curved into a loop to have meaning. Its meaning is in its balance. Its story is in its endurance. The stillness between stars isn't a pause in the music of creation. It's the music itself, slow, steady, infinite. If you close your eyes for a moment and imagine all of it, the galaxies drifting, the light stretching, the space expanding smoothly without edges or breaks, you might sense that stillness yourself. It's not silence, it's continuity. It's the soundless hum of geometry remaining constant while everything within it changes. The stars are temporary, but the space that holds them is forever. And in that space, in that calm, in that endless balance, is where we live. The stillness between stars isn't just what fills the universe, it's what gives it shape, it's what makes it whole. And as the universe continues to expand, flat and infinite, that stillness will remain, gentle, patient, and eternal,